Hi, good morning.
Hi.
Hi,
Morning.
Lauren. Morning. I just want to make sure everything works remotely.
It does.
I just updated the slides a little bit in a few minutes ago. I hope that's the latest. But it doesn't really matter if it just a couple of lines update.
Are you able to upload them?
Yes.
Well, but in BBB, not in Indico.
Okay. That's okay. It's not a big change.
Let me try to. I think I'll give you. I don't know if you're able to do that, to be honest. Yeah, I should be able to. I made you presenter. Just try to the plus button. You should be able to have a look at the slides, and you can upload them and delete the one I just uploaded.
Okay.
Give it a shot. Or you can send them to me and I'll do.
Yeah, I just uploaded, but it's not just 2 lines of change. I think it's okay either way. Yeah, but I will need to know how to share. So right now I can control, right? Yeah. Okay.
In the plus button, I think you should be able to manage slides. I mean, you can delete what we are currently seeing and upload the new ones.
Okay. It's only 2 lines, so I don't want to risk, just some technical. It's good enough. I mean, yeah. And maybe after the presentation, people will see the correct one.
Yeah. Can start. Morning, everyone, and welcome to the VFIO IOMMU PCI MC. Before starting, I would like to take an opportunity to thank Krzysztof, who is online, without whom this microconference wouldn't have been possible at all. So, Christo, thank you very much for making this happen, and thank you very much, everyone, for attending it. Well, I will not speak for too long. I mean, the microconference is split in two halves. The first one is PCI based, and the second half is IOMMU based. There is a short break in between, half an hour, as you might have noticed in the schedule. And without any further ado, I'm handing over to Jakob for the first presentation. Thank you.
Thank you. Should I flip the slide?
I can do that.
Oh, I mean, I just need to see the first slide to start.
Use the plus button. You can just select your slide, your presenter. So.
Oh, okay. Okay, got it.
Good.
Okay, so yeah. Hi, everyone. I'm Jacob Pan. I work for Intel. And in the past few years, been working on IOMMU, but this topic is also x86 as well. So it's good to see some x86 people in the room. So thank you for attending. First, I want to acknowledge the people on this project. And I'm not trying to pronounce all the names because I may not get it right. But for all those, also for those ones I can get it right, but you may not recognize who I am talking about. So thank you. So I started working on this project because one time we were working on a performance debugging case, and then one of our cloud engineer told me that when you have a lot of new Gen 5 NVMe disks attached to your to the same socket, our performance just dropped so quickly. So we were looking at the issue. It turned out to be interrupt related. So this topic is about how to improve interrupt throughput and making new use of the old technology, which is posted interrupt on bare metal. So just a little background, IOMMU interrupt remapping has been turned on by default because the X to APIC support. Oh, by the way, feel free to interrupt. It's better to make this interactive. And so VTD has already, most of the other IOMMUs, I attended the RISC-V talk 2 days ago about IRQ bypass, and they all support remapped mode and the posted mode in some form. So the posted mode today is only used for virtualization where MSIs for a directly assigned device can be delivered to the guest kernel without hypervisor intervention. Oh, sorry, this slide is old. Okay. I updated the slide with some more diagrams. Sorry, this one doesn't have it. But I'll just talk through it. So the hardware flow to deliver interrupt is a continuous flow from the device to the IOMMU, and IOMMU fetch the translation, and then send a notification to the CPU. The CPU deliver that interrupt to the OS handler based on this vector and the interrupt descriptor table mechanism. And so this flow is continuous in hardware flow without software touch points. With post interrupt, the first two steps, the hardware, the interrupt generation and acceptance into the system agent or IOMMU is the same. But what's really changed is that the interrupt delivery become two parts. One is posting to the memory, and the other part is send a notification to the CPU. The notification part actually can be controlled by the system software as needed. So the software can control when and if the notification is sent to the CPU. So this is through a memory resident descriptor that both IOMMU and CPU can touch So the problem with that today is that when the interrupt arrives in a very high frequency, the remappable interrupt we have today is very inefficient. If the CPU is already busy with processing interrupt handlers, and then the IMU still keep notifying, there's more and more. It's kind of like driving a whole bunch of people, 5-year-old to the zoo, and you're already driving at a full speed limit, but they're still keep asking, are we there yet? Are we there yet? It just doesn't help. It's just a distraction, and they're gonna slow you down. So another problem with that is the notification part of the CPU is very slow, at least on Xeon, and I could think about actually a, a song called "A Long and a Winding Road" because I can't really describe the microarchitecture details here, but it's a slow and expensive process. And also the MSI writes has a strong ordering requirement with the DMA writes, and all these combined as a result is that the IRQ rate has become a limiting factor for the IO performance. So the slower the IRQ, the slower the DMA. So we measure that on the Sapphire Rapids, which is the latest Xeon platform, and we attach 2 and 4 at the bottom line here, 2, 4, or 8 disks for the same socket, and then we use FIO out of the box, basically libaio benching to measure the IOPS. You can see with two drives, and the performance is about at the line rate as 2 million IOPS per second per disk. When we have 4, it drops to 1.1, and the 8, it drops less than half. So the performance drop is very very significant. So the proposal or the solution that came up with this RFC patch I recently posted is that since our system software, the kernel, is given the ability to control when and if the CPU notifications are sent. So basically, we could coalesce those notifications while the interrupts are coming at a high burst or high frequency. So that's making a new use of the posted interrupt capability. So we call it posted MSI and then coalesced interrupt delivery. So I want to illustrate this through this timeline here. The time flows from left to right, and the high-speed MSIs arrive in high-frequency burst groups. So ABC here is in one group, and the D, F, G in another group, and the HI, they are more sparsely arrived. So with a remappable interrupt on this RI row here, every single one of those MSIs will generate a notifications, even though the CPU is already, say, busy processing MSI A, but B and C's notifications still sent to the CPU. So that's kind of the the are we there yet? Are we there yet? Kind of notification, and also it goes through this long and winding road, so it's very slow. And with post interrupt in this patch, what we wanted is only for the leading MSIs of each burst, we allow a notification to be generated to the CPU. So it's a less interference to the CPU processing. So as a result, all the N and the right prime notifications are avoided. So this basically essentially, just coalesce those notifications. I want to kind of pause for a moment because that's kind of the key idea of this optimization. So the posted interrupt is not exactly, just a simple replacement. There's some subtle differences I wanted to mention here. So all the MSI vectors here being multiplexed into one single notification vector. So from the CPU point of view, from the APIC point of view, there's no more MSI, device driver MSIs arriving at the CPU directly and going through the IDT delivery, interrupt descriptor table delivery. Another change is that post-interrupt, we lose some of the features that remappable interrupt supports. For example, in remappable interrupt, you can say, I want to deliver this MSI as a NMI, non-maskable interrupt, but here it's not a choice. But I don't think we're using it today. The only thing I know about it was some effort to do HPAD deliver as NMI for watchdog timer, but it's not in upstream. And also the delivery destination is physical only. That's fine with MSI because it's a unicast anyway, so you cannot do cluster. And another interesting thing is that now the MSI vector space is actually a separate namespace than the APIC vector. So it's not subject to the local APIC restrictions where you have restrictions for the low and the high. The low is the the legacy interrupts and the systems, and the high is like high is the system interrupts like timer and other things. But it's still to really separate the vector space is a very intrusive change. So in the RFC, I didn't really do that, but it's in theory is possible. So with the RFC patch, Ben, I'm sorry, anybody has questions?
Question for you, Jacob. I'm sure this is obvious to everybody else, but if you back up 2 slides.
Yeah.
Yeah, here. So you're eliding the MSIs. So the OS will only see basically the first one. So the MSI indicates completion of some DMA, right? So there's another mechanism, I guess, to make sure that, for instance, MSI C, that transfer is actually completed. How does the driver know that has been completed?
It's still completed in order. It's just actually it's not the MSI being coalesced in the PI line. It's not the same as the MSI. It's a different vector. It's the notification vector. It's not the actual device MSI's vector. So it's.
But it happens at the time of MSI A, right?
Yes, and then MSI, and then the post-interrupt, the MSI vector gonna go basically poll the memory to see which device MSI is pending, and then go process still in order. So from the driver point of view, it's transparent. I have the more detailed slides in later. So
yeah. Okay. I figured. Thanks.
Bjorn, I think what you're looking for, Bjorn, is that you want to see that the N prime, the excess, the last, with coalescing, you want to see the interrupt delivered with the last one of the burst, not with the first one. Is that correct?
You want to see them in order, right? Yeah, I think that's guaranteed. I have the slide to explain later. It maybe become more clear.
So I think Bjorn's concern is because of the ordering. Drivers assume that the data that they were, the IRQs, the strong ordering that you mentioned in the first slide or previous slide was because data has to be visible in memory to the CPU that's handling the interrupt. That's the assumption of MSI, right? And so if you are delivering the interrupt earlier than the original IRQ, there's a potential for out of order interrupt handling. It's
not really delivered early. It's just being, how can I say, it's still in order. So it just we'll try to only process the next one after we finish the first one. So there's no out of order. So I have the pseudocode and the trace later on to explain this. Yeah.
Okay, thank you.
Bear with me. Sorry. Yeah. Sometimes code is easier to see. Yeah.
Why do you need posted interrupts to do this? Couldn't you just scrub through the IRR and pull out pending interrupts before enabling IRQs if your goal is just to reduce the number of actual IRQs that are delivered to the core?
Yeah, the thing is that the expensive part is delivered to IRR. That's the notification. So that's the long and winding road, and at least on Xeon.
Yeah.
So we try to avoid. Yeah.
The whole point of this optimization is to stop delivering to the IIR because that's the slow thing in.
Yeah, I had in my later slides. Sorry, I
It
just
serializes the MA between the IOMMU and the CPU.
sorry, can you say it again?
Sorry, I was answering a question in the room. Sorry, so the question was about delivering to the IIR and why that's the thing that we're attempting to optimize with this plan.
Yeah, that's
So,
more
carry on.
kind of microarchitecture thing, and yeah. So I forgot. I think that's so with the patch, and we remeasure the same FIO, LibAIO test on the same Samsung Gen 5 NVMe drive. And the first row was 8 drives on the same socket. And then so before and after, we gain quite a bit performance. Basically, they all either 8 drive, the first row, and then second row, the 4 drive, and they both can recover back to the line rate of 2 million IOPS per second. And then we also have a separate test I made based on the built-in data streaming accelerators. This way you can pump millions of interrupts per second and from different devices, and also set IRQ affinity to the same CPU. And you can see similar significant gains in IRQ throughput with this mechanism. So this is the RFC patch here. And but we do notice that, I mean, I guess from the hardware point of view, both CPU and IMMU are doing atomic exchange to the same cache line to update this memory location where interrupts are posted. So those are kind of expensive operation we try to avoid, but we have not seen any downside of turning on for every devices on the system. But we're continuing evaluating, especially at the lower interrupt rates, less than 1 million per second per CPU. We're not seeing any difference between this patch with or without this patch. So here is one of the implementation choices I like to discuss and get some feedback, help to get it more clean. And the first is I made this choice to be, transparent to the device driver. All the changes to just stay in x86 and IOMMU code. And so also the interrupt mode switching between remappable to posted is a per interrupt option. But so that means you can do, per device as well, or system-wide. But I made a choice to be a system-wide because it's a lot. First of all, you don't see any downside to make it system-wide, and also when you have more interrupts, there are more chances to coalesce. So you can coalesce between vectors, not just the vector itself. Keep posting, but I did exclude some of the legacy devices and also the IMMU's own IRQ because it's not posted. It cannot be posted. And because in the loop we could be getting an interrupt storm, we keep polling for more, and there's always more to handle. So we wanted to limit the number of notifications for polling, basically DMAX loop. Each time you get a notification, so give a chance for other things to run. And I have some data to show like what it would be the optimized the max loops. And so the changes are also limited to, in terms of interrupt domain, it's limited to the Intel or the interrupt remapping chip where it has some changes, but it has no impact to the PCI, MSI, and the device drivers. So far, this changes also x86 Intel only, but I'm not sure this can be extended to other architectures. We'll also have posted interrupts. I think ARM and the RISC-V, and they'll have that similar capability. Even though it's made for virtualization, but I think the memory file or memory resident descriptor has the HPA, the host physical address. So I think there's no restriction that it cannot be used on the host. But I'm not sure. That's why I need help. And I look at AMD spec a little bit, and it seems they're pointing to the virtual APIC, or so that's why I need some feedback from other architectures.
So on that in particular, what AMD, you have to point to the virtualization structure that ties the virtual APIC IDs of the vCPUs together. You may be able to instead point that back at host state, but there's definitely more of the virtualization bits involved in the delivery of the interrupts after you've posted them into memory.
I see. Thanks.
You've been measuring IOPS and seeing significant improvement, but what about latency? I'm thinking about what happens when you do when you call these networking MSIs, for example.
Yeah, the latency, FIO give you the latency, the completion latency. We didn't see any much difference. The reason is you can see from how this works, actually, from this DMAX loop, how it works. So when you have, interrupts MSIs, say from network device or NVMe comes to the system, and they all got basically collapsed into this system vector, notification vector. So there's, no matter you have 200, but it only comes as one. And then inside this loop, inside this, we first, do the prologue IRQ, and then start this polling loop, and basically do an atomic exchange to get what's pending in the memory, the posted interrupt descriptor. And then if it's pending, then we will call the IRQ handlers one by one for each bit is set. So if it's nothing pending, then they will just continue and just exit out of the loop. And then so there's no wait for more. Say you have to call, let's say 5 interrupts or 3 interrupts. So there's no wait. So in that sense, the latency is just whatever it takes to execute those handlers. There's no additional latency added. I think some of the device firmware coalescing scheme, they have to wait for a certain number of interrupts. So this way it adds some tail latency. But this case, it just continue. Does it answer your question?
Hi, I have a question. Have you compared this to the scheme where the device sends the MSI, but then it needs to be rearmed before it will send more? I think the interesting thing about that approach is that the device will not be spamming MSIs. I think in your scheme, all the MSIs are still being sent by the device, and then they're basically being coalesced later. Yeah, so I was curious because I think some network cards do that. So what do you think about that approach?
Yeah, actually, I've just seen my backups. Like the NVMe has some tuning parameters to set coalescing there, but first of all, it's per devicing, so you can only coalesce device itself. But here is more a generic scheme, so you can coalesce across different devices vectors. It doesn't care, and also it's it doesn't need to wait for more. It just, if there's nothing going on, and then it just naturally just continues. It will be returned to the same behavior as posted interrupt. I mean, as a remappable interrupt. Maybe that does it answer your question?
Kind of. Thank you. Yes.
Yeah,
So one thing.
4 minutes. Yeah, if you want to have, if you have questions for the audience, I mean, I think then you need to stop. Sorry.
Okay.
Go ahead.
Yeah. Thanks. So if you run this patch, you're going to notice there's a new IRQ chip, and that's called IR post. And also in terms of interrupt accounting, there's one more in the proc interrupts for the notification interrupts. So if you compare the number in the PMN post MSI notification versus your MSI account, you can see the ratio is the coalescing ratio basically. And when I showed this proof of concept to Thomas Gleichner, he pointed out there's an issue with this approach, and I'm still working on. But basically, is that before this patch, the interrupt on the left, arrives individually. So you handle the prologue and call the handler, and handler does the EOI, and then just every interrupt is separate. So even though we don't allow preemption within the handler, but system, high priority system interrupt can still get in between. But with this approach, in the demultiplexing loop, we just call the handler, one by one, without allowing, system interrupts to come in or soft IRQs. So that's adding some delays in the loop. So that's one of the challenges. I have made 3 attempts to address this issue. First of all, since this patch is that we basically limited the number of polling loop can be done. So with the data showing that even if it's just coalesce 2, 3, 4, I mean up to 3, you already got 90% of the benefit. So this is just an IRQ injection test. And actually here I was trying to correct this, that 1 means 2, one max loop 1 means 2 coalesced, because after the coalescing loop, we have to do 1 more round to make sure there's no leftover interrupts. So just by collecting 2, 3 interrupts, they already got 90% of the benefits. So in the RFC patch, I just set it to 3, and possibly we can make it tunable, but it's probably easier just have a reasonable default, and we don't have to worry about it. And another attempt is try to make this notification vector, a notification handler, preemptible. And so basically inside the handler, I'm going to re-enable the interrupt, local interrupt, and I had a disable interrupt here. So the runtime trace would look like enter, and then when you re-enable the interrupt handler, it happened to have say a timer interrupt, so it will be able to preempt your notification vector. But because we have collapsed every other MSI vectors into one, wouldn't be any nesting other than this one. So the nesting only 1 deep. So we don't have a problem, I think, with the IRQ stack overflow. And I thought that was the main reason that we don't allow interrupt, nesting. But in here, we have only 1, just 1 deep at most.
Jakob, I'm sorry, I need to ask you to wrap up. I don't know if there are questions from the audience or anything you want to ask. Just go for it. Anything else you want to get from the audience? Any questions?
I think that's it. That's pretty much the last one. The third one is not really the using IPI is not really a good option. It's just nullify the benefits. Yeah. So.
Any further questions? I think you can take it offline then. Thank you very much, Jakob, for your presentation.
Yeah, thank you.
Mani, you're in presenter mode whenever you're ready.
Thanks, Lorenzo. Let me select the slide. All right, let's get started. Hello, everyone. Welcome to the PCI Endpoint Subsystem Open Items discussion. I'm Manivanan Sadasivam. I work as a senior kernel engineer at the Qualcomm landing team of Linaro. So in the past, Kishon used to drive this discussion, but since he moved on to a different job, he passed on the baton to me this time. So this is the agenda for today's discussion. So the first item is VFIO EPF drivers for interoperability. And then the second one is device integration with endpoint subsystem. And then the third one is using Genlock framework for managing the output window memory in endpoints. So the items 2 and 3 were carried forward from previous year because they didn't get materialized. So I thought of presenting them this year also to get some consensus and then move forward with the implementation. All right, let's get started with the first topic. So, okay, before moving into the topic, I would like to give a quick overview of VFIO. So VFIO is an open standard for communication between drivers and devices of different types, which means VFIO offers a standard communication between two entities, and one entity will expose the device and another one will just consume the device. So this VFIO specification was initially developed by Rusty Russell for his own hypervisor called LGuest, and so there he used the VFIO for managing the communication between the hypervisor and then the guest operating system, which was Linux. Now the specification is maintained by a standards body, which maintains the specification and also improves them over a period of time. So since VFIO was initially developed for the hypervisor use case, it is primarily used in the virtualization environment for exposing the I/O devices to the guest operating system by the hypervisor. And today, VFIO is not only used by LGuest, but also by other hypervisors such as KVM, Acorn, etc. And over the period of time, the use case of VFIO has evolved outside of the virtualization environment. So it is now used for other use cases like interchip communication within the SoC. So we have the RP message framework in the kernel, which is based on VFIO, and it is used for talking to the multiple core processors inside the SoC. So this is the simplified architecture of VFIO in a virtualized environment. So where we will have the hypervisor and then the guest operating system in an SoC. So the hypervisor will expose the emulator devices to guest operating system. And as per the VFIO specification, we have a backend driver running on the hypervisor. So it will expose VFIO devices based on the hardware it wants to expose it to the guest operating system. And those VFIO devices will be consumed by the front-end drivers running in the guest operating system. So one really good thing about VFIO specification is that it offers independency between these two entities, which means a single hypervisor can run with any sort of guest operating system, and the guest operating system can run with any type of hypervisor. So which means if you are a hypervisor developer, then you need not worry about the guest operating system exposing the front-end drivers, and you can just develop the back-end drivers for exposing the VFIO devices to the guest. And this is one of the reasons why we were considering adding the VFIO support to the endpoint framework that I will cover in the later slide. So let me give a quick overview of the PCI endpoint subsystem in kernel. So traditionally, Linux has been used on the host PCs, like PCs and servers. And you would connect a PCI endpoint device to the host machine in the PCI bus, and the host machine will be running the Linux operating system, which is completely open source, and then the endpoint devices will be running some random proprietary firmware. But if you want to run Linux on those small PCI endpoint devices, then you need to use the PCI endpoint subsystem in kernel. So it is added as a separate subsystem under the PCI hierarchy. And there are two entities in the PCI endpoint subsystem. The one is endpoint controller. So these endpoint controllers completely manage the PCI transport on behalf of the endpoint subsystem. So all of the PCI endpoint controllers supported in mainline are device tree based. So we don't have any ACPI or BIOS. So these PCI controller drivers need to manage all the PCI transport interactions like enumeration, allocation of resources like IRQ, memory, etc. And then the second entity is endpoint function driver. So these drivers define actual behavior of the device. Let's say if you want to develop an NVMe SSD, PCI-based NVMe SSD, with the help of endpoint subsystem, then you need to have a dedicated function driver here, talking the NVMe protocol to the host, and also managing the non-volatile memory on the device. So we can say that the endpoint function drivers are the heart of the endpoint subsystem. And like any PCI endpoint device, we also need an equivalent driver on the host for exercising the full functionality. So right now, the mainline Linux kernel exposes, has the PCI endpoint test driver and on the endpoint, and then we have one equivalent driver on the host called PCI endpoint test MISC driver, and this driver will just exercise some basic functionality of the subsystem, not suitable for production. But as I said in the previous example, if you are developing any NVMe-based PCI cards, then we just need to create one PCI endpoint function for the NVMe, and then we can make use of the existing host driver without any modification, because it just follows the NVMe specification. And hey, that's the advantage of using the specification type. But the problem is we don't have specification for rest of the devices. Even if there is specification, the devices don't follow it. And that is another reason why we wanted to go for VirtIO-based endpoint function drivers, because there is a standard for VirtIO in place. So the idea for using VirtIO in the PCI endpoint subsystem moved around 2019 with a patch from Haoshen Wang. I hope I'm pronouncing the name correctly. If not, please forgive me. So the use case of, the idea of using VirtIO in the endpoint endpoint subsystem is to make use of the existing front-end drivers on the host. So in the previous slide, in this slide, we can imagine we can replace hypervisor with the PCI endpoint device, and then the guest operating system with the host machine. So these two will be connected over the PCI bus. So this guy will be called, will be implementing the backend driver, and this will be implementing the front-end driver. So with the help of VirtIO, the PCI endpoint developer can just focus his time on developing the backend drivers for exposing the VirtIO devices to the host machine, and we can actually make use of the existing front-end drivers available on the guest operating system. It can be Linux, Windows, or OpenBSD. So this greatly reduces the fragmentation because we need not develop our own device driver in the host, and it also reduces the lead time drastically because the endpoint developers can completely forget about the host and focus the time on the endpoint development. So we have received 3 proposals so far for adding the VirtIO support in endpoint subsystem. So I'm going to present all of them and pick one of my favorite. And if you have any questions, feel free to interrupt. So the first proposal is from Haoshen Wang. It was back in 2019. So I have presented the proposal in this picture. So we have the host and endpoint devices connected over the PCI bus. So on the host machine, on both host as well as the endpoint, we have Linux kernel running. And on the host, we have the VirtIO net front-end driver, and that is talking to the VirtIO PCI legacy driver. So the reason for using the legacy PCI transport was because of shortcoming in the endpoint subsystem, because the endpoint subsystem doesn't allow you to write to the the vendor-specific capability registers. That's a requirement for using the modern VirtIO PCI transport. So because of that reason, the legacy was used, and then it talks to the PCI subsystem, and that controls the RC. So this entire host side is unmodified in this proposal. And the only modification is there in the endpoint. On the endpoint, we have the PCI endpoint IP that is controlled by the endpoint subsystem, and we have the VirtIO EPF driver. So this was the driver introduced in this proposal. And this driver exposes the VirtIO net device to the host machine, and also one local VirtIO net device to the endpoint. So you might wonder why we need a second local VirtIO net device on the endpoint. So the reason is just because for the sake of development, because when we want to use this proposal in a real life product, This block will be replaced by an actual IP like a modem DSP that will be transferring the data packets in and out of the word queue managed by the CPF driver. So, but if you want to just get your hands on this implementation, then we need to have some sort of user interface, right, on the endpoint. So that's the reason the second VFIO net device is exposed here, and that will bind to the VFIO net driver. These two are actually same drivers available in mainline. And this will expose a network interface to the endpoint, and this guy will expose one more network device on the host. So these two, with the help of this, the user can actually talk to the host main point over PCI bus. They can use IPO for any kind of network utilities for testing, benchmarking, etc. So this was the proposal from Hawashin. So in this proposal, only this driver was introduced, but this driver turns out to be very complex to review because it was exposing two different VFIO devices and also managing all the word queues by itself. So this proposal didn't move forward. I think the author at the time was an intern, and then he went back to his school, so he didn't get any attention afterwards. So here comes the second proposal from Kishon. So Kishon, being the maintainer of endpoint subsystem at that time, so he proposed his own VFIO solution. He actually discussed this in the previous Plumbus conference itself. So in this proposal, he has actually introduced one driver on the host side, compared to the first proposal where the host was unmodified, but he introduced one VFIO PCI EPF driver for talking to the endpoint. And on the endpoint, he introduced the vhost EPF driver. So vhost is traditionally used for offloading the data plane data plane handling from the backend process like IOMMU in a virtualized environment. But since the code is already there and it is used for handling the word queues in the host, Kishon thought of making use of them. So he introduced the vhost EPF driver, and also he modified the existing vhost library in the host, in the kernel for as per the kernel device driver model, so that the vhost EPF driver can bind to it. And he also made use of the existing vhost net driver. This is a client driver actually, and this vhost net driver is managing the VFIO net device that is being exposed to the host machine. I think the idea of using vhost for this implementation was just to make use of the existing vhost library, so that we can go for some code reusability. But unfortunately, this proposal also didn't get merged. There were some discussions, good discussions between Kishon and the VFIO maintainer at that point of time, but I think they didn't reach any sort of conclusion. So this proposal was also kind of left on.
So just to add a comment here, right? So my major use case at that time was really to have a RP message based communication between two devices. So previously, like automotive vendors were using RP message for communication between two cores within the same SoC. But as part of a requirement, they also wanted to extend it to use the same RP message protocol to communicate between two independent cores in two independent SoCs. So that's when this was started. So one of the things that I had to use for using the vhost was really because you have this front end which has which actually manages the VFIO ring, and then you kind of have a shared mechanism to kind of access that VFIO ring from the back end. So vhost kind of provided that interface basically to access the V-ring in the front end, and that's why it was really started. So basically my major use case was to use RP message. As part of that, I was also thinking it could potentially be used for VFIO net, which was initially introduced by Hawashin.
I mean, I actually used VirtioNet because, I mean, it's all same, right? In your proposal, you have used RP message, I know that, but I just wanted, for the sake of comparison, I just used VirtioNet in the diagram. Yeah, thanks. So the next and recent proposal was from Shunsuke. This proposal is almost similar to the first proposal from Haoshan. And the only difference is he made use of the VDH helpers that is actually part of the the vhost library. So he used the VDH APIs for offloading the word queue management of the front end. So the word queues are the fundamental building blocks of VirtIO, right? So it is used for transferring the data between the front end and back end. So the word queues will be created by the front end, and the endpoint of the back end needs to manage it. And in the first proposal, all the handling has been done by this driver itself. And as Kishon said, he wanted to make use of vhost for offloading those word queue management. But in this proposal, he used VDH APIs, Shunsuke, for offloading the entire word queue management. So this is the key difference between proposal 1 and then 3, but the rest of the functionalities are same. This also exposes the network device to the user space on the endpoint as well as on the host, so that both sides can communicate with each other. So in my opinion, I'm thinking about moving forward with the proposal from Shunsuke because the proposal 3 seems to be simple and also scalable one. Let's say if we want to add support for VirtIO SCSI in the future, it can be done easily because it should be noted that this EPF driver has been split into 2 parts in this proposal. One is the common VirtIO library that has abstracted all the VirtIO implementations. And then there is one VirtIO net EPF driver that only takes care of creating the VirtIO net device for the host as well as for the endpoint. So if we want to add support for VirtIO SCSI, then we can add one more EPF driver, VirtIO EPF SCSI, and then make use of the existing the VirtIO common library. And then compared to the proposal from Kishon, I think even though vhost allows us to make use of the offloading the word queue management, I think that is kind of achieved using VDH in this proposal. So that makes me feel like having the vhost implementation is somewhat overkill, and it also adds complexity to this overall implementation. And the first proposal is not going to fly because everything is handled within this VirtIO EPF driver. So, and that made the real driver really messy. It's hard to review and it's not going to be maintainable.
Hey, sorry to interrupt you. Oh, the question I was going to ask is, in a world where hardware offload via VDPA is available, especially considering how much that has progressed with VirtIO Net, what value do you see this adding over, either VDPA or another approach that kind of wraps SRIOV versus the implementation you're describing here?
So I'm not too familiar with VDPA. Sorry for that. So I have to check on that. Sorry, I'm not familiar with VDPA implementation.
I'm not the expert on it myself, but it's kind of the idea is you kind of leverage SRIOV to offload at least queue processing to the NIC, and it sounds like here you're trying to achieve a similar thing by having the NIC firmware speak effectively the VirtIO kind of config and setup protocol. So and there's a lot of hardware out there already in the SmartNIC ecosystem. I know that even the ConnectX line at Mellanox is supporting a lot of this stuff already. So I'm just kind of curious, like with that as an approach versus kind of building out this new PCI transport layer, if there's any, if there's been any. I mean, clearly, since I don't know if there's been any discussion of it or if any of the maintainers have responded. If not, and no one else wants to continue the discussion. Sorry.
Well, this is obviously for hardware that has an endpoint mode but does not have SRIOV. So there's a ton of hardware that has endpoint modes, but that wouldn't be able to do this thing because there's just no SRIOV. This is very simple endpoint hardware that is very widespread, and then you can use something which is better than nothing, but it's
And that's mostly for prototyping because the performance is not that great with this.
I think that I asked for the throughput measurement from Shunsuke, and he shared that he was able to achieve less than 1 gigabits per second. Yeah, the performance is not that good, but I think that can be improved. And there are also a couple of issues. One of the issues is that currently we have to poll for the notification from the VirtIO host because we don't really have any mechanism for when the host says driver okay, the endpoint cannot get any notification for that. So we are just polling that specific register continuously in a while loop, waiting for the driver okay. So these kind of shortcomings are there, and we are looking for ways to address them.
So I'm very interested in this work. In the OpenAMP project, we're also looking at something like this for on-chip SoC, but it's so that we can take any VirtIO protocol and make it work this way. And so, the endpoint may be a small Zephyr system, an x86 host with a full ARM system SoC on a PCI card. So net isn't the only applicability. If we can find something where VirtIO in general can work in this kind of an AMP system, has applicability in lots of places, right? So, and yeah, I mean, actually a gigabit is interesting in edge cases and IoT cases. So just because it doesn't apply to the server doesn't necessarily mean it's, not interesting.
And for the polling problem, the issue is that the controllers are just too dumb that they don't say anything when the host is writing to a bar or sending something. There's no interrupt, no nothing. So the only solution is to poll currently. That's a hardware problem.
Right, but there is also one more workaround that we are discussing in the mailing list. So we can actually map the interrupt controllers, the MSI area to the bar, so that when the host writes to that interrupt controller's MSI area, the corresponding IRQ can be triggered on the endpoint. So that's a patch that's already floating, but I don't know if that can be used for this use case. But,
well,
the
really other simple would be to have a generic polling for that stuff. I mean, every single driver is implementing the polling itself, which is kind of a bit silly. So we could have generic polling for events and stuff changing in the bars or whatever.
Yeah, that's one other option.
So in my opinion, right? So the approach by Shunsuke looks fine, but I think in addition to VirtIO net, we should really. So I still have to see what is the driver model that is being used. How do you tell whether it's going to be VirtIO net or like a VirtIO console or SCSI or whatever it is. But I think in addition to having a symmetrical or the same driver on both sides, something like VirtIO net where you can use both sides, that could be like asymmetrical protocols could also be used. Like for instance, RP message is like an asymmetric protocol, right? So you kind of like have like a different driver on the host and a different driver on the endpoint. It's not same, but it would complement each other. Probably VirtIO block could be something like that because one end would be writing and the other would just consume it. Right. So how it scales is something I would really be interested in. And the other point I wanted. Sorry, go ahead.
Please go ahead. Please go ahead.
Yeah, so the last point I wanted to make is the VirtIO is actually, so as you mentioned, right, it is a lot driven by the standard. So if we are introducing like VirtIO EPF, I think I would assume that would have its own register map protocol itself. So in that case, we should also try and add it in the OASIS or the VirtIO standard, the link that you showed earlier.
I don't really think that's necessary because we are already following the standard. I don't know what's so special with the VFIO APF driver.
So the VFIO, so the spec really says the register map or the address map. At this offset you give this ID or whatever it is, right? So the VFIO PCI has its own its own set of standard standard registers. I would assume that because when I initially proposed my solution in 2020, that was one of the feedbacks that we got in the LPC, because I was introducing a VFIO PCI EPF, which was kind of like slightly different from VFIO PCI, so which means I have to add that standard. So looking at that, comparing it with that, looks like the VFIO EPF is something that's new that you are planning to add, right? So in that case, that should also be standardized.
No, so I just went through the code. I didn't try it on my hardware fully yet. But as far as I can see, this is just following the VFIO PCI standard, and it just exposes whatever the registers that are defined by the spec in the bar region. So I don't see really any difference between that and this.
Okay,
so we are just following the specification.
Okay, if there is no difference, I think then that should be fine.
Yeah. Thanks.
Manny, you've got 2 minutes, so I think if you want to...
And then I do have 2 topics to discuss, but I don't think I can cover them. So the next one was device tree integration for the endpoint function driver. So I don't think I can cover them. I mean, let me just give a quick overview of this. So the endpoint function driver currently has no device tree support because they are just software blocks. They're like the endpoint test driver, which just simulates some registers on the bar region. But we have one odd driver called EPF MHI driver. So MHI is the Qualcomm specific protocol for transferring the data packets between PCI host and endpoint. So if you are using any Qualcomm-based PCI endpoint devices, then most likely you'll be using MHI. So this has a hardware backend in the SoC itself. So I would like to, add a device tree node for this MHI function because it's there in the hardware and there's nothing software based. So this is the proposal. So the endpoint, so the MHI function will be a child node of the PCI endpoint controller, which is already there. And it will have some properties like reg that denotes the function number, because we can have 8 physical functions in an endpoint, and the function name to identify this one. And then we have the property for specifying the bar regions to be used. And this is going to be a 64-bit array because the endpoint can support multiple bars. And then the interrupt, so the MHI has the facility to trigger doorbell from the host. So whenever the host writes to some specific registers on the bar, the MHI hardware can receive the interrupt from the PCI bus. So for that purpose, we need to have the interrupt property as well. So this is my proposal for adding the device tree node.
I think we've got to wrap up, but I think it's a good question because next is Rob coming up. So I mean, maybe you can answer straight away.
Yep.
I don't know anything.
Thanks.
Any last questions for the audience, anyone? Anything you want to ask?
No, that's it. I think I got the solution. Thank you.
So thank you very much.
Thanks.
Hey, Rob, whenever you're ready, I mean, be all set. You can flip the current slides. Yeah, thanks.
Rob, you are muted.
How's this?
Better.
All right. Good morning, everyone. Lizzie and I are here today to talk about non-discoverable devices behind a PCI device which is discoverable. I was supposed to be there in person, but somehow I got the conference called before the conference. Anyway, so what's the problem? This is something that's come up from time to time. It's actually not just PCI, but today we're just focused on PCI. But modern PCI devices are more than just a device. There's can be a whole slew of devices contained within it. And the discoverability is somewhat limited in PCI. You have the vendor ID and device ID and not much else to go on. And in some cases, devices are in there is not even fixed in the case of FPGAs. So we have solutions for how to discover non-discoverable stuff. And one of the things is we want to be able to reuse existing drivers for those sub-devices. And we need a solution that works for both the device tree and that other firmware interface, ACPI. So there's been a variety of devices and use cases that have come up over the last couple of years. This is a somewhat complete list, I think. First is AMD's FPGA based PCI cards. Lizzie's going to talk about that in a second. Another one is Microchip has a Ethernet switch SoC that can be a PCI endpoint or run as a standalone SoC. There's a testing framework called Road Test that was submitted a while back, and they were trying to do platform devices behind a VirtIO PCI device. Greg saw platform device and basically killed that until I pointed out that MMIO devices in device tree are platform devices, and we used to have that separate and combined it. And anyway, they went on with a different solution, I think, for that. Jonathan Cameron, I think he was in the room earlier. I can't see now. Has a use case with testing CXL. As I understand it, it's adding. Someone trying to talk, or no? As I understand it, it's basically adding BMC SoC devices into the emulated host directly rather than through the BMC interface.
Rob, I can add a little more detail on that. This is a more general thing for QEMU that if we want to mess around with, should we say, a weird mixture of a standard platform and pluggable devices, and we don't want to build a board model, then it's awfully convenient to use the fact there's a PCI adapter and then add stuff to that. So basically it gives us a pluggable interface to standard board in QEMU is the side of it.
Right.
So a weird mixture of discoverable and not.
Yeah. And the last one is probably more a hobbyist, deep embedded kind of use case with FTDI serial chips. Some of them have I2C and SPI and GPIOs hanging off of them in addition to serial. So you could have anything on those interfaces, and none of that's discoverable. And then say you want to plug in multiple of those to your host. What do you do? That's not PCI, but it's still a similar problem. Now I'll turn it over to Lizzie to talk in more detail about the FPGA PCIe card.
Hi everyone. My name is Li Jiho, and I work for AMD. Today I just introduce our IOMMU PCI device as a use case for this topic. First of all, you might be already familiar with this modern device structure that our device expose multiple hardware peripherals, and they work together to finish the job. For example, our card contains DMA engine or maybe UART and other devices, and each of the hardware peripherals work independently, and most of them already has a driver in the platform driver in the Linux kernel, and we want to leverage that. And also how to access this individual hardware peripherals. Those are being exposed on the PCI bar. So as long as you map the PCS to the CPU access to the IO map, then you can use the existing driver to access those peripherals. That's the whole picture. And also we are, as Rob mentioned, our card is also FPGA card based device, so it's partially reconfigurable. That means even with the same card, if you reprogram a different FPGA image on the card, then it can become a very different hardware. Look at the picture. The card initially has a function, has a peripheral A and B exposed on the bar 0, but later on, if you program another FPGA image, the location of A and B can be different, and it can even add more hardware peripherals like C exposed on the bar.
I think Rob will flip slides.
Thank you.
Yeah.
Based on this hardware facts, we definitely need a data-driven peripheral discover to discover this non-discoverable device exposed on the bar. So as I already mentioned, that can be different FPGA being programmed on the same IO device. That means PCI bar numbers and size may be the same, but the peripherals exposed on the bar can be very different. And the images, the different images can be just a bug fix or change a little bit things. So it's not feasible like you can hard code something in the driver that won't be scaled. And also considering all these facts, so instead of introduce another way to describe those peripherals, we think why don't we just leverage the device tree, which is very mature and being accepted in the Linux world. So what we did is when the hardware team generates the FPGA image, there is a device tree section along actually inside the FPGA image. So to describe those peripherals in the image. So currently we are still using an all-tree driver which do parsing or create the platform devices by the driver. But assuming this effort is success, then there is a device tree node for the IOMMU PCI device. Then we can leverage all those cool device tree functions to just overlay the device tree binary to the under the IOMMU PCI device. Then all the platform device will be created automatically. The driver will be plugged automatically.
So you don't really need a device tree node to do the overlay, right? We can fix this so that it works even on non-device tree platforms.
Sorry?
You don't. You just said you need a device tree node for the PCI device in order to do the overlay.
Right.
But we can fix that, right? That's easy enough to make that work on a non-DT platform.
Ultimately, you do need a node. Whether it's real or fake is the question.
So if you want to add device to children, you need a parent device that corresponds to the PCI device.
But we'll get to that on the last slide.
Okay.
Okay, so the last bullet is about the benefits for using the device tree. So the device tree obviously is very popular in the Linux world, and it's very successfully described all kinds of hardware. And also the FDT is very compatible format, so it won't use a lot of space in the FPGA image. And device tree also provide a good infrastructure like sysfs. We can dump all those things at the runtime. And also in the FPGA world, there is already combined with the device tree to describe FPGA region, which actually can be dynamically programmed. So that's our use case. So we think the device tree is a good fit for our device. Thank you.
Thanks, Lizzie. The other use case, microchip folks, well, Bootland folks are working on this device. My understanding of it is, okay, we have basically a standard SoC, a bunch of cores, a bunch of devices, PCIs, host is also on it. Nothing unusual there. It's all described by device tree. Everything works. But this same chip, you can essentially turn off the CPUs, use the PCIe as endpoint mode, and access all those on-chip devices over PCIe directly. So ignoring ACPI for a second, how would we solve this on device tree? Well, that's pretty straightforward, actually. Describing PCI and device trees been supported basically forever. Open firmware systems like Power, the firmware populates the DT with the PCI devices before it hands off to Linux. In flattened device tree, PCI devices in the DT are usually either something soldered down, and it's also generally just small additions to the DT, like adding a MAC address for a Ethernet or Wi-Fi device, not a whole tree of devices behind it. And this is also the case of having a bus behind PCI is just isobus, really, which has also been supported forever. And we have a way to dynamically add onto device tree with DT overlays, and that's already supported on FPGA devices with the FPGA subsystem. So there were two main issues to solve here. One is that normally we don't have a node for PCI devices, and for one, the location may not be fixed. So the solution there is that we're generating or can generate DT nodes for PCI devices as they're discovered. And that was added in 6.6. Right now it's hidden behind a kconfig option, and long term that needs to be runtime in some way. There was another issue with address translation from the simple bus back to the CPU's bus. The issue there was just in the DT address translation logic and supporting a format with 3 address cells, which currently was just PCI before that. That's also added in 6.6. So we have a solution for DT. What do we do for ACPI? Well, why not the same thing? What are the gaps there? We need a base DT to apply the overlays to. We actually have that already with the DT unit test on any system. When that's run, we have a base DT. Right now, it's tied into the unit test, but there's also another use case with KUnit wanting. Stephen Boyd was looking at adding tests for the clock subsystem and needs to add test DT nodes. So there's patches that have been posted to separate that out, where you always have a base DT. Also on ARM64, you always have a DT because the boot interface to pass the kernel command line and initramfs is always via DT, even on ACPI. We need to have the PCI device DT node to apply the overlay to. Well, we added that with what I just talked about. We need, but we need a host bridge node, and that's the part that's missing. What are some of the problems? There's lots of assumptions that we have either a DT node or an ACPI node. So what happens if a device has both? And then the other issue is, how do we map interrupts, MSIs, IOMMU, any translation there from DT space to ACPI space, kind of. I think there's kind of 2 options there. We keep generating resources in the generated DT until things work. Or the other option is make the DT or the PCI device driver that's doing all this figure it out and do the right thing. What about, there's also ACPI overlays. I'm told that's a debug feature currently, at least. And it doesn't solve reusing drivers. So questions? Let's see, skim through some of the chat. Seems there's some agreement.
Yeah,
Hi. So I worked a bit on the microchip LAN stuff. And one of our problem that we had with issue that we have with GT overlays is actually the dynamicity of PCI. You can plug and unplug the device and so on. And there is actually some ref counting on the device nodes, which are actually not used at all when you don't have config OF dynamic. And also you don't have any ref counting of properties. So do you have any plans to address that, or is something that you encountered while testing that?
Well, node ref counting is such a mess. We should certainly add property ref counting to add to that. I'm not surprised there's issues there, because it's the node ref counting is hard to get right, and I don't know, other than we have to work through the issues and solve that problem. That's a big reason why we haven't supported overlays with a generic interface to apply anything. The kernels can't.
Yeah, for the ref counting issue, I don't know if you can hear me.
Yes.
I tried to fix quite some of them, and also on creating the DT nodes for the PCI devices. I've got one issue. I have a local part. I have to send it upstream. Is related to the strict device. In fact, we're going to have some device with the strict device and firmware node and an OF node attached to this strict device. Currently, in fact, when we create the OF node for the PCI device, we do that with the overlay and we create a new strict device. And I think we have to reuse the existing one, which was created by all the PCI system. To avoid a kind of duplication of strict device node.
Yeah, offhand, that seems like that would make sense to me. I'm hearing some background discussion or something. Can't tell.
I think somebody's in a room. They need to mute their mic. Hey, Rob. So have you thought about how you discover the DT overlays? Is this UDEV kind of rules that pair a device to an overlay sitting in the file system somewhere? Or is there a PCI config extension where you can put a DT fragment?
That would be a problem for the PCI driver to find and load its overlay. So in the FPGA case, I think it's part of the FPGA image. So when you're programming the FPGA, you get the overlay and then you load that. And I think the rest of the FPGA subsystem uses the firmware loading interface to load the overlays.
I think if we are going to do this, there's some stuff on this in the chat. If we're going to have drivers around this, it will be helpful if someone defines the config space stuff, maybe to point to a bar where you can read it from. Because with a bit of luck, everyone won't then have to reinvent the wheel. And there are ways of doing that, but someone needs to donate an ID.
Wouldn't it depend on the hardware?
Oh, sorry.
Sorry.
The option ROMs are there, right? You turn the option ROM bar on. The option ROM format has, identifiers for the type of blocks in the option ROM. You could just define an overlay type in the option ROM. I mean, all that stuff is standardized already.
Option ROMs bring a whole pile of other rubbish that we really don't want to deal with.
That
No.
assumes it's fixed as well.
All the problems around hotbug, and they're not usable for many cases. I mean, it might work. There's nothing wrong with allowing that too.
It assumes that it's fixed as well, which is not the case for FPGAs.
Yeah, that's true as well. There is an assumption that it's not changing on you. There's loads of ways we can solve it in a nice generic way. Oh, another op.
For FPGAs, you can also just bake it into your bit stream, right? And have like a per driver fixed offset you read it from. I don't think that's crazy or even, not maintainable, because you'll anyway have an FPGA specific way of loading it. And a standard PCI thing doesn't work for that, because like you don't necessarily take down the config space or something. So
there's loads of ways around that. Just put a mailbox in there. So what you're actually doing is pointing at either a DOE or something else, at which point you can put whatever you like behind it.
There's a question on the chat from Laurent. Will x86 distros agree to ship a kernel with config OF equal yes? I don't have an answer. Build it and they will come. I don't know.
There's SSDTs in ACPI, right? I mean, what's the difference between that and the ACPI overlay? Just basically adding it in and ADRing it based on where it's at in the hierarchy, the PCI config hierarchy.
That's the ACPI overlays, right? That's what they're loading. They're going to be worse off on the ref counting, as I understand it, because there isn't any. Maybe it'll be better.
And yeah, when you consider the solution of the ACPI overlays, actually a lot of subsystems that are exposed by, for instance, the microchip LAN card are not supported. So you don't have ACPI support for such subsystems. So we didn't consider this solution just because we would need to add ACPI support to these subsystems. I think it was maybe we had some I2C, SPI, timers, clock. It's like a full SOC system exposed through PCI. So which is not usually done, let's say, with SPI description.
I think time is up. Rob, any last question for the audience? Anybody? It's always fun, ACPI, isn't it? So.
Well, if the biggest discussion point was where we loaded the overlay from, I guess that's the win. Thank you.
I think we are taking a break, restarting in half an hour. So thank you very much. Right. Thank you.
Check. Checking 1, 2. We're all set. Is noise incoming? Not so bad. Cool. The sound that came out of the speakers wasn't, at least I don't know if you were.
But the point is, the system, if it's muted, it wasn't like this when I came this morning. I don't know what changed. So if you are unmuted, I think there is an echo. I don't know what. Maybe Mike, you know, I don't know.
Yep.
But the point, if you see there, if you are muted,
Yeah. So we got it? What happened?
thank you.
Okay, cool.
Ask a question or maybe you see, the only way to flip slides is what? It's by these should work. No, they don't. No, they do. Clicks over. Oh yeah. No. Sometimes. No. Ah, this is annoying. Okay. But it's fine to click here. It's not a problem. I mean, for some reason it keeps mouse there. Maybe I should take presenter here. No. Yeah. No, it's you gave presenter for one of the video streams. No. Maybe regarding the entire, I'm not sure it's a good idea. No. Sorry. No. So I think it's time to restart, and just handing over to Pasha for the next section. Thank you very much.
Okay. Hello, everyone. So I'm Pasha Tatashin. I work in the memory management team at Google. And I'd like to talk about several problems that we encountered in the last several months related to IOMMU page tables. And propose some solutions to those problems, and also have a discussion about how to address some of them. So the first few slides are going to be about observability and accounting, and then we will talk about stability and debuggability, basically ways we can quickly debug problems that are related to the IOMMU page tables. Okay, so growing IOMMU page tables. So at Google, we are trying to categorize the kernel memory overhead. So we try to find out where like we are trying to reduce the size of the hypervisor, as I guess everyone else in the industry, and we are trying to explain how the uncategorized kernel memory is actually used. Also, we had some problems where we're starting seeing some IOMMUs, and we knew that the problems were coming from our hypervisor being larger than expected. So it took us some time to actually find out, like to explain what was happening. And the problem was that our IOMMU page tables were much bigger than we were expecting. In fact, they were actually many gigabytes in size. And when you're trying to reduce the hypervisor to be just a few gigabytes, that is, of course, not acceptable. The machine where we saw that was AMD, and I wrote a small program that reproduces it by basically doing DMA maps, DMA unmaps, and verifying that, and cycling through the VA space. So basically, we on map pages, the page table entries, the page table levels do not have any valid entries, but we never free them. And I thought that it probably just AMD driver implementation, because we never saw this problem on our Intel and actually on our ARM machines as well. But then I ran this program. It's called IOVA Stress, and there is a link to GitHub to this program on all three machines, AMD, Intel, and ARM. And behavior was exactly the same. So we basically, as we cycle through the VA space, the amount of free memory is reducing on all machines. And you can see it's reducing about the same size, because again, because there is no observability, we don't have a way to look at this, to look directly at the size of IOMMU page tables. The way I was looking at the overhead was just by looking at the amount of the free memory, and as you can see, it went down on all three architectures. So the reason why we didn't see that on Intel and ARM was basically by accident, because the hypervisor slot was larger on those machines compared to on AMD. Now, the question is, why would we even cycle through the VA space? That's the implementation detail of the of our userland program that's doing that. But I think that overall it is a good idea not to reuse the VAs for the security reasons. I mean, there is a reason why we have address space randomization, and if we always reuse the same VA, why would we even use IOMMU? We could just use direct, like one-to-one mapping. So my point is that we probably should have an ability to actually use different VAs every time without tearing down the domains. So the proposal, so as a quick fix, we changed the program not to cycle through the VAs, and we also were thinking to have a quick fix in our kernel where we would just free the page table levels on unmaps. But that is inefficient because you would have to check if page table is all zeros at the time of unmap. So a better way would be just to use ref count to have the number of entries at a particular page table level. And once it reaches 1, so it's just allocated by IOMMU. At that point, we probably want to add it to a free list and free it sometime later asynchronously. Yes, and please interrupt me at any time, and let's. I want to have a discussion. So
sure. So there's a conversation on the mailing list right now about the Chanfrost DRM driver. Who, anyway, they want something kind of similar, and I actually sketched out on the list how to do this, and a reasonable API that would fit into like VFIO and IOMMU that would fix your situation. So it's mostly just waiting for someone to actually want to do it. But there's several now several reasons why we'd want to do it. Like this has been a known problem for a while.
Okay, so are they fixing it for all IOMMU implementations? So or is it just we need to do it separately for specifically for IOMMU page tables, and that is separate from that discussion?
So this is one of like my pet peeves about the IO page table sort of mini framework we have. It's not. It goes as far as letting you share some of the code between a DRM driver and the IOMMU driver, but it doesn't let you share algorithms between IOMMU drivers and between different IO page table implementations like you can in the MM. And I think it would be very valuable if somebody went and restructured that so that we were sharing algorithms and the IO page table was just providing like the radix tree, bit manipulations and things like MM does, and then you could have a generic implementation.
Yes, so that's actually one of my proposals is actually to move all the page allocation functions into a separate file that is going to be reused by all IOMMU architectures, and then in that file also manage the freeing of the pages, but we probably need to have a thread that does that asynchronously, because I don't think that we want to do it synchronously.
Honestly, unmap is already so slow and map is already so slow. You're chasing the wrong thing if you're worrying about threads at that point. There's way lower fruits to get to before you get to worrying about threads.
I mean, it's slow today, maybe will be faster tomorrow. Do you want to make it slower? Because
well, I'm just saying, like, so once you fix the IO page table stuff so that it's kind of using generic algorithms, and one of the first things you'd want to do is fix unmap so it wasn't so horribly broken for what IOMMU wants to do, so that you could make it actually run fast. And then after you do all of that, then maybe you'd want to think about, is freeing a page back to the page allocator my hotspot? Like, probably not.
Yeah, so another concern that I have about like freeing page table levels is that there are some libraries that actually try to reuse VAs. So if we do freeing on every single unmap, we will slow down those libraries. So perhaps we should start freeing from the back of the queue, so not immediately, And that's why the reason why I was thinking to have like this free list and do it from like.
It really depends how expensive it is to allocate and free from the page allocator. And again,
yes,
map and unmap are already very, very slow. There's so much going on there.
True, but that's just another thing to consider.
How do the user space page tables handle this? Surely you have the same problem.
So I haven't looked into the way user page tables handle that, but I would assume you use ref counts for that. And if anyone here has the answer.
So you're asking, like, what does the MM do? I think, if I remember properly, the way MM works is kind of similar, and they have a similar problem. It zaps basically all the PTE levels under a VMA, which is exactly what IOMMU, or at least the good IOMMU drivers do. So his issue is specifically because he's using 2 meg, basically 2 meg VMAs. And I think people have talked about like cleaning up PMD levels and other levels, but I don't know. I remember seeing it at LSF once. I don't think it's gone very far.
It's not only about PMD, right? I mean, if you unmap 4K and it's the last 4K on the bottom level, you want to remove that level and the level above.
Yeah, definitely. But I don't think the MM does that optimization unless your VMA spans it already.
Right, but here, like, if we know that it is the last page because of the ref count, we can just add it to a free list, and then once the free list becomes large enough, we can start freeing it at sometime later.
So the reason why the code is how it is that page table updates are encouraged to be lockless in the IOMMU code, because otherwise it would be a big bottleneck for massively parallel I/O operations which use DMA API.
Mm-hmm.
There was lots of work going into the IOVA allocator with per-CPU magazines and everything to make this actually parallel and per-CPU, and we don't want to have another bottleneck in the page table code that if we allow page table page freeing would need locks. So we need some fine-grained blocking to actually make it still scale, right, across multiple CPUs. Even if it's slow on a single CPU, it needs to scale with the number of CPUs.
Yes.
And the ref count is not the whole solution, because even if the ref count is zero, you don't know whether another CPU comes around and is about to update it again. So you can't atomically check ref count and unmap the page from the page table.
No, right. I don't plan unmapping it immediately. Again, that's the reason why I'm suggesting to put it on a free list, but keep it in a page table until we actually do the hard job of actually freeing that page sometime later.
So the proposal in the mailing list addresses what George was talking about. Like, we don't want to disturb the DMA API, and we want to keep the kind of nice lockless behavior that it has. So what I suggested is that you could manipulate the ref count like on request. Like, you could reserve IOVA in advance, and that would pre-populate the radix tree and also depopulate the radix tree based on ref count. So you would provide an API where you could either be like DMA API where you're lockless and you're kind of weak, or you could be like VFIO where you want to be strong and you want to have ref counts. And we could put them both into the same algorithms and not hurt DMA API like that.
Yeah, that is the goal. I certainly want to keep those page tables lockless, like, so doing only the atomic operations, and so not to reduce the scalability in any way.
Well, I don't see a way to keep it lockless when you are starting to unmap page table pages. I'm not sure whether RCU is the solution. Probably some fine-grained locking, like what the core MM code does, doing a PMD level lock or something. That would probably solve the problem. Then you can free the leaf pages, which already should give you a much benefit, or should solve this problem to, I think, 90% or so.
Mm-hmm.
RCU works fine. We do it in the MM in a couple of places. The way you do the RCU, yeah, you free the page, you free the radix tree page under RCU or with an RCU free, so it's deferred. If you reach the page when you're walking and you try and get a ref count and it's 0, then you know that some other thread is freeing it, so you just don't touch it. And you're doing that on your RCU, so that ref count check is safe. And then you basically store the new page. So everybody has to be a little careful when they're updating the pointer to that level. That needs another atomic, I think, but it works out, and it's a slow path anyway.
Okay, so another thing that I wanted to consider is, do we want to have any kind of control from the userland in terms of the maximum size of this free page table levels, or do you want to just have it automatic? I see one opinion that everything should be automatic. Okay, so but if it's automatic, then will we just set it to some default value, like a couple megabytes in size, overhead, or what is it going to be?
I think the point that was made is just like, as soon as you free it, it's on the RSU free list. It's going to get free. You don't have it anymore. So you don't have like a free list that you want to have. It's no longer yours. You do RSU free of the page, so the page is already free, so you don't have a list.
Yeah. So if but that would mean that we do it inline, right, during the unmap.
Yeah.
So you think that we shouldn't do any kind of? Okay, I mean, that would increase the time to do the unmap. So, but
No. If you do RSU free, it won't increase the time to do the unmap. That's the idea.
Well, I mean, maybe not in terms of locking it won't increase, but in terms of just extra stuff doing. But adding pages to free list is actually also some extra cost. Yes, okay. So you're thinking just putting it back to the body allocator and just right on it. Okay. Well, I mean, I could try that to do some measurements, see how it impacts the performance.
So I was just curious. So I've worked on MMUs in the past, a long time ago, so I'm a little bit out of date. You guys haven't talked at all about the TLB that's typically in an IOMMU to cache the translations that is looked up for the DMA that's happening. Have you guys taught? So the TLB shoot down was actually the most expensive part of an unmap, and that's why we would coalesce them into batches, and that's why the unmap was so expensive. Has that changed, or is there something else?
You're worried about the wrong thing. The doesn't do that kind of stuff. It goes back to the buddy allocator. The buddy allocator is pretty fast. The big overheads are the TLB shoot downs and all the other stuff, like pinning pages, the unpinning pages. There's so much junk in that path that we can optimize before the allocator is going to be the critical.
That is exactly why I was thinking to do that in a batch. So we do the one flushing and then freeze several pages at a time instead of doing it every single unmap.
We have infrastructure that can do that. We're just not.
Yes, we do have infrastructure to do that. That is exactly that. That's why I was saying that. Do we really want to do on every single DMA unmap to free a page table level once it's become free? And that becomes expensive, isn't it?
I would say it should go in the gather like does, and it should be freed when the gather is flushed like does. So from your perspective, from like a VFIO user, when you do unmap, it gets freed. But internally to the kernel, we'd want to batch the entire VA range that you're trying to free and optimize like does. Like it's not any different than
Oh, okay, so just basically piggyback to the flashing function. Okay. Yeah, that would work. So basically, I guess when we flash, walk to the page table, look where we have ref counts 1, and then just free those as well. Yeah, that would work.
There are actually two parts of this, right? There's a part where we're keeping track of the page we need to free, and the part where we do actually the invalidations. And the invalidation can be batch with ranges, right? You don't normally have to do invalidation on every single page individually, right? So I think in the invalidation part, I think we can kind of figure out how to do it efficiently. But I think like the conversion going back, it was actually like how do we track those pages, right? In the PMD and the last level before we can figure out like do we need to call the free for those pages. I mean, invalidation is a separate things here.
So that depends on who you're talking to. So if you talk to the security teams, they want invalidation the moment it becomes free. They do not want them batched. Before it goes free, sorry,
free, yes.
But I mean, the driver says, I'm done with this page, and now I want to invalidate it, and it becomes free then. Yes, correct. Sorry about that.
Worse than that, like some of the hardware has caching of radix tree levels, so you have to invalidate the hardware before you go and free the page back to the buddy allocator. Otherwise, the hardware, like the IOMMU hardware itself, is going to start doing use after freeze, which you don't want. It is in the hardware. No.
Yes, and actually there are different modes, right? With the DMA, you can do lazy flush, you can do non-lazy flush. If you care about security, then you do non-lazy flush. But in this case, I think security, they're already taken care of by having the IOVA spread it out so that you will not be reusing IOVA. That's why we run into this problem, because the IOVA space is getting so huge. And then at this point, we need to figure out, okay, if that's the use case, how do we do the free, right? Yeah.
That's okay. So another question is, Jason, maybe you can answer too, is anybody still measuring utilization of ILTOB? How efficient is the ILTOB? Is the caching effective or not? Because one of the suggestions here was you have a generic page allocator for the IOVAs. And very often the IOTLB policy is what dictates how you allocate the page address space, because then you don't have IOTLB collisions between DMA streams on different physical pages and such. Right? There can be utilization issues around that. In the same way that processors that have virtually tagged caches also have like page coloring and other schemes to avoid cache collisions.
I think we can determine that by using like IOMMU has performance counter, right? To count how many times the TLB is actually hit or miss. So I think before we can answer that, we need to determine that first and then see if that's really the problem.
I mean, I don't have data to share, but I know, certainly as a device manufacturer, we look at IOTLB efficiency quite seriously, and we consider, the size of the ILTOB relative to what kind of workloads we're running to run. And we know that ITLB misses are incredibly expensive and very harmful to device performance. As for like coloring and things, I think at least the modern enterprise IOMMUs have TLBs that are fully efficient like the CPU. So they don't have bias. I mean, I'm sure they're multi-way and they have collisions and things, but we don't seem to take care of that in the software at all. We just don't do anything. Interesting point. As far as I know, all the big ARM, the 2x86 and ARM, I don't think they have, but that's a micro architectural detail. I don't know. All I know is that we have no software that tries to address that.
Okay. Thank you for the discussion. I'll take a look at the patch, at the discussion that you mentioned, and I think the first attempt is going to be to do the freeing at the time of flushing. That's basically sounds like the time when that is already expensive, and let's do everything at the same time. Okay. Okay, so for the observability, we have ProcMemInfo, where we have a lot of statistics for the pages that are managed by body allocator. And we have page tables and we have secondary page tables, but we don't have IOMMU page tables. So I'm proposing to add another field, IO page tables.
So this is just for the whole system, right?
This is for the whole system, yes.
I think it might be more useful to have it per VFIO container or something like that. So especially if you're in a VM, if you've got VMs, you can know which one is consuming your IO.
Sounds good. So we probably want to do that as well. So this is more for observability, like in general, so users can quickly see where the memory is used in the system.
But unless you know where it's coming from, right? Which VFIO container? What
I agree. I like this proposal.
But it's not only VFIO related. I think the problem is mostly seen, or the problem we are trying to solve is mostly seen in DMA API domains, right? It's not in VFIO domains. Because VFIO domains are set up with the GPA to SPA mappings, and there are not many unused page table pages, right? I think the problem mostly occurs in DMA API page tables. So and these are not covered by a VFIO container. So either we have it per device or per IOMMU group or something. Yeah.
IOMMU group device over there. Okay.
John wants it.
But that would also mean that we would have a different counter. So, and I will talk a little more about observability later, and I will explain why we still want to have this counter in addition to what you're proposing. Okay.
So for the counter, please just reuse secondary page tables. The entire reason it's called secondary page tables and not KVM page tables and not vert page tables is for the IOMMU to piggyback that. So just put your accounting in there.
But what if you want to have them separate to see the problems like this?
This comes back to James' point, though, where if you want to drill down into that level of detail, you have to have it tied to something that's not system scoped. These are useful. So KVM does do all of its accounting and tracking, and we have per page size counters for how many pages each VM is having. A bunch of junk around that. The system-wide stuff is still useful because it allows you to detect things that like, oh, we've gone off the rails and we've got a systemic problem. So that is super coarse-grained. If you want the gory details of what a specific VM or IOMMU group is doing, then yeah, you have to have much more fine-grained specific counters. But at the system level, coarse-grained is good enough.
Fair enough. So I'll modify Procman Minfoot to report the sum of for the EBTs and IOMMU page tables, because we will still track them separately within the system. It doesn't make sense to have like a node state page increment the EBT counter for the IOMMU page tables in the system, right?
I didn't quite follow that.
So actually now thinking about this, so we have this zone counters, and that zone counter is incremented. It's incremented for the EBT page tables in the KVM.
So what I'm saying is, so the secondary page tables, which is your coarse-grained system scope thing, use that for all secondary page tables. So anything that's not the primary MMU, throw it into secondary page tables, which is basically KVM and IOMMU at this point. And maybe some GPUs if they wanted to throw something there, but that seems unlikely. And when you go below that, then it becomes subsystem specific, how you're surfacing stats and accounting to user space. Like in KVM, it's per VM. And you can also surface those up through KVM as a whole, but mostly what you're looking at is for this VM, what are my stats? And there, what you care about is not necessarily just how many page tables have I created. You're caring about how many page tables at what level have I created. Because if you have 10,000 page tables, that may not be interesting. If you have 90% that are 4K, that can be very interesting relative to, oh, this VM over here has far better performance because I've got 1 gig across the board.
Okay. All right. So I'll add the statistics into the secondary page tables, and I will look into how to report per IOMMU the main statistics.
I would encourage you. I actually welcome adding similar, like KVM has per KVM counters, add per IOMMU FD counters someplace as well, and that will do. You could do a lot of great stuff with that. I think that's a really great project for someone.
Okay. Good suggestion. Thank you.
And I don't know how many counters you want to add into the IOMFD and if you want to like consider those ABI, but other things that from a KVM perspective that we found useful are how many entries you've zapped. So even if you're just looking at how many page tables you've created, if that stays relatively steady state, but then you have something that's just goofy and you're constantly zapping and recreating, that can also cause performance blips. And if you are just tracking how many you have, but not how many you have churned through, it's harder to see. So that's another one that might be useful.
Yeah, I'll take a look at the statistics that you provide, so that KVM provides. Oh, what in the chat? I cannot scroll here for some reasons. It's not working. I've been trying to scroll. It doesn't work. The question in the chat.
And there are a couple of questions in the chat. I don't know if they're referring to the latest discussion. Isn't the reason for IOMMU besides catching bad software security? Yeah, no, well, I wouldn't say they're stale. I don't know, but I think it's we missed them. So.
Just to sort of preempt your slide, I think I already got this merged like 2 kernel cycles ago, so it's already done.
So IOMMU, like now all page Alex actually charged?
For IOMMUFD, yeah.
For
And
IOMMUFD?
maybe VFIO, I don't remember if I did VFIO.
I think the kernel like a week ago, it's definitely not counted, this as a week ago.
Definitely did a lot of VFIO too. I don't know if we did every, like the DMA tracking the objects we have in type 1. The question was, did we put it in IOMMU map? I don't think so, because the only allocation we have in type 1 there is that DMA, VFIO DMA tree. I don't think we're counting that one yet.
So I tested earlier today, and I think I think my kernel like most a week ago, maybe less than that, and yeah, so accounting is still not there, at least for what I'm proposing. Yeah, to add accounting it is indeed, but we also want to add this page state function that actually increments. If you want to have IOMMU page tables accounted separately, right? And I think it makes sense to have like a separate accounting specifically for, like we have CPU accounting. We have like, it makes sense to have a separate IOMMU page table account.
I don't really want to reuse like some weird MM thing, because I want to keep the LRU available for some of the other stuff we talked about at the beginning of the talk in the struct page, right? I think it would be great if C group had a way to partition, to bucket the source of the allocator for debugging. It's a more generic feature. Like, I don't know that we should be doing something specific to IOMMU here, is what I'm saying. Like,
okay,
like C group, if you want to break down the C group where it's going, then that's a C group question, in my opinion.
In that case, it is indeed going to be very simple change, just add kernel accounting and be done with that, not adding the IOMMU specific controls and reporting. I like it. It actually makes things easier for me. Okay, so another problem that we've had in the last several months, and is that we've seen some memory corruptions. They're not necessarily IOMMU page table related, but the thing is that over time our systems became more complex. Now a page can be mapped in user page table, in kernel direct map. It can be mapped in IOMMU page table. It can be mapped in the extended page table. So there are many different page tables. And when we find the memory corruption, and we usually find memory corruptions by accident, for example, like ext4 file system can find it through journaling, or during the live migration, we can find when we check summing before and after live migration. We know the physical address of the page that was corrupted, but we don't have a quick way to look where that page is mapped. So in the system. So we could, of course, ignore the kernel mappings, direct map, because like everything is mapped there. But it would be interesting to see if that page, like the one that was that is corrupted, if it was mapped in any of the IOMMU page tables, or any of the extended page tables, or something like that. And for user page tables, we have page map. We can just go through them. But we don't have anything like that for the other page tables. Do we want to have something like that? And that should be, if we do, it should be fast. It shouldn't it should provide an access so that if we have an error that this page is not actually mapped at the time, but it reports that it's mapped, it's okay. We can tolerate that kind of errors. But the point is that it should be fast, lockless, and just something that where we can quickly check where a physical page is mapped. So for several reasons, there is a window the page can get unmapped, and we don't want to slow down other processes that actually using those page tables when we do the lookup. So it's a memory corruption, for example, in a virtual machine, right? We kill the virtual machine, but we don't want to kill the whole host. We want to continue running, but we want to look at where that page was mapped at the time of the memory corruption.
So my original question was, why does this need to be fast? And I'm just thinking, you had a memory corruption event. You should take all the time in the world you need to figure out what happened there. I don't think it needs to be fast. That's not a fast path. It's not a regular thing that happens. It should not be a regular thing that happens. If it is, there's something else wrong with the hardware.
Another comment.
Instead of fast, do you mean it should not disturb other things going on in the system? Because those are, I agree, like you don't need the lookup to be fast. And unless you have reverse maps, the lookup is not going to be fast, because if you've got a VM with a terabyte of memory, have fun walking all the page tables to dump a terabyte of memory. It's not going to be fast, but you don't want to disturb other systems. So it's not clear what the requirement actually is.
The requirement is not to disturb the other system. So it should be lockless, and since it's lockless, it
doesn't have to be lockless though. I mean, it's like if your lock is scoped to the VM that just died, who cares?
But you're not looking inside the VM. You're looking so the page was corrupted. Someone else corrupted it. It's mapped somewhere else. We want to.
Yeah, no, I got it. All I'm asserting is that when you're saying it has to be fast and lockless, you are putting a line that you don't actually have to meet. You don't want to take locks that may be contended by something other than the process that you were trying to debug. But it's totally fine to take locks that nothing else in the system should hold. So
sure, I can. Confusing. Yes, if that line is confusing, I can rewrite it to explain it better. That makes sense.
Pasha, but you've got 5 minutes just to say if there is anything you want to go through. Just keep it in mind.
I think there's just one more topic.
So I don't know if you're aware, but Intel driver has a debug.fs that does exactly this. I think it would be a great idea to make it general, like my previous comment about making the IO page table stuff more uniform. It'd be great if we had a debugfs that worked everywhere consistent.
Does Intel driver actually has like a page map like interface? So I mean, because I don't think it actually dumps the entries.
It's not the same. It's not the same, but it gives you the same data.
You can extend Intel's debugfs interface to show that. That's one way to do that. But do we want to do that there, or do we want to have it somewhere else? Like I mean, every single process has a page map. Do we want to have that for every VFIO or something?
There was a previous attempt on SMMU v3 driver as well to add the debugger support. So that was very specific within the driver, and the comment was to move it to IO page table. Yeah. So and I think that we were trying to add some support for stream table printing and all those stuff as well, like dumping all the information. So.
And to extend to that, do we want to have a similar interface for extended page tables as well, to be able to so page map basically for extended page tables?
Just want to point out, like, there is a security issue with that also. So, keep in mind that from a security point of view, it needs to be a lock.
Yes, I understand.
When you say extended page tables, are you referring to, is it mapped in KVM's page tables?
Yes.
So I would say don't bother, because the way KVM works, the page tables are ephemeral and they may or may not point at guest memory at any given time. User space has mem slots that has explicitly told what virtual addresses have been mapped into the guest or are available to the guest. So you can just use the proc page map to cross-reference that. Trying to dump it from KVM is probably going to be a bit pointless.
Okay.
All the information you need to get what KVM may have mapped is available already to user space. Adding more into KVM is just
unless there is a bug, and there is a bug. We know there is a bug because there is a memory corruption. And if the two maps are not synchronized correctly, then that's not true.
The problem you have with KVM, though, is that you don't have one EPT.
Yes.
You have, for the lifetime of VM, you theoretically have infinite number of EPT routes that you could have used. So I just don't know that it gains you much. I'm not necessarily against it, but I just don't know that it gains you much relative to what you have today. Like, I think to get something like that landed upstream, especially, I would want to see some concrete use case you ran across where you found memory corruption that you couldn't resolve, and the only way you could resolve it by was knowing exactly which mappings at that snapshot in time were in KVM, and you couldn't get that with a crash dump.
Okay, so it's only 2 minutes left. There is one more thought for enhancing the stability and debuggability of the. It's more actually about stability. So we have this page table check functionality every time when we insert a PT entry into user page table. We check that PT entry is not at the same time, for example, mapped as anonymous and file, or as anonymous read-write, but to several processes and so on. So it's a simple rule. Like table of rules, and I copy-pasted these rules. And the question is, can we extend that to other page tables, to the secondary page tables? And if so, what kind of rules could we add there?
Quickly, we already have this in KVM. We have a variety of rules, the legal transitions, the combination of bits, variety of things. Some are warn-ons, a couple are bugs, some are protected by expert-only kconfig that only KVM developers are expected to turn on. So we have a variety of.
So when you insert a page into the, so the way page table check works, it works outside of the regular So it's not. It tries not to rely on the memory management data structure. Instead, it has its own extended page table field where we count how many times this page is mapped as named, how many times it's mapped as anonymous. So the question is, when we map into extended page table, we know that this, like if that page is mapped as anonymous into the user process, it shouldn't be mapped anywhere else at the same time. Or if it's already mapped as like into some EBT already.
But that's not how KVM works. If the whole scheme of KVM's mem slots is that if it's mapped into host user space that's associated with the VM instance, it can be mapped into the guest.
I understand that, but
they're two different domains. You have rules for how KVM and IOMMU presumably can manage memory and what the transition rules are and how that ties back to the primary MMU. But I don't think you can take anything that you're asserting on generic MM and the rules for anonymous memory versus well-known memory and apply those to a secondary MMU, because the entire point of a secondary MMU is to be able to reflect stuff from the primary MMU into something else.
So again, this is like a separate state machine. It's not relying on the actual.
But what I'm saying is we have that in KVM to enforce KVM rules.
Mm-hmm.
And I don't know how you can go beyond that without making things up.
I'm sorry to stop you, Sasha, but
yeah, I'll take a look at
you can
the.
wrap it up, and if you wish, I don't know.
Yeah, I'll take a look at the extended page table. I mean, at EBT's rules. Thank you, everyone.
And thank you very much.
Very good. Right. Okay, I guess we'll just get going here. So my name is Jason Gunthorpe. I'm going to talk about IOMMUFD. Kevin and others have been working on it. They were unable to attend. Kevin, Nicolin, Yi, Eric, a few other people I've probably forgotten. But I'm here representing basically the whole team. So I was going to start with like a quick review of what IOMMUFD is, what it is, what it's for, what we've accomplished in the last year, what's left to go, and kind of some of the discussions on the mailing list that haven't maybe fully settled, because some of them are kind of difficult. So this is my slide from last year. The purpose of IOMMUFD is to let us access all of the advanced hardware features that people have built into the CPUs and expose it to the VMM, expose it to QMU, let us build virtual IOMMUs that we can plug into guests, and then we can have higher performance guests. We can have guests with more features, like we can have virtual SVA support in our guests, which enable modern hardware to use all of its abilities. This is very similar to what VFIO does, and it's kind of tightly wound to VFIO in a certain way. It originated from we sort of extracted the container code from VFIO and put it in IOMMUFD and made it shareable to wherever it needed to be shared, and much more focused on modern kind of IOMMU design compared to the container approach. So to sort of reemphasize that picture, this is what a classically, probably what the most common IOMMUFD configuration would be. You'd have VFIO using the brand new CDEV interface to access a VFIO device. So the CDEV interface means you get a dev/dev VFIO/ like VFIO1 is a specific PCI device. You can open that CDEV. You don't need to use groups. You don't need to use containers. That's the only UAPI now that VFIO presents that you have to use. And you open yourself an IOMMUFD file descriptor, and you connect the two together with a bind or an attach. And in the future, we'll also have to link KVM into this too, because there's IOMMU hardware features that become linked to the KVM hardware features inside the processor going forward. So we've developed a bunch of new features, and we kind of have this language now that relates to the IOMMUFD objects. I've written this from the perspective of a VMM, from something like QEMU, but it's just as valid for something like DPDK or any other kind of non-KVM based application out there. So when you open your VFIO device and you attach it to IOMMUFD, you get back a device object. In a VMM case, the next thing you probably want to do is you want to make a IOMMU map that's an identity map of the VM. So this means you're basically mirroring the KVM memory map into IOMMU. So you create something called an IOS, most likely an IO address space. If you want to start like a shadowed VIOMMU emulation like Intel has, then you'd create IOSs and hardware PTs for every DTE or ST or whatever your hardware emulation is. They basically represent a PGD pointer in x86 language from the guest. They'd represent a guest PGD pointer, and you'd walk that page table and you'd shadow it into IOMMUFD, and you get this handle for it. For nesting, you would allocate this thing called a nesting parent, which is essentially very similar to the EPT in KVM land, where it's the identity map of the guest physical address space. And then you can create an accelerated guest IO page table, which we're calling a nested page table. So this is a page table where the actual IO PTEs reside in user space memory, reside inside guest memory, and it's translated by hardware with a 2D translation similar to the way KVM does it. This is done on the IOMMU hardware in this case. So to access this feature, you create a hardware page table, and you give it a hardware page table ID referring to the identity map that would have been created in the nesting base. And going forward, we're talking now about guest support for PASID. So PASID is the PCI ability for a single PCI function to have multiple IO page tables. So in PASID mode, the guest can have a whole bunch of IO page tables, and the VIOMMU now has to sort of relay PASIDs through the infrastructure. Every PASID points to an IO page table, which is created with hardware PT. And PASIDs probably, I don't know if anybody's going to bother doing it with a shadowing technique. I guess it's possible, but it's not that useful. So we're imagining it's probably only going to be used with nested, but that's not a UAPI constraint. That's just probably what people will do. And we also have DMA dirty logging. So this is the dirty page tracking. It's similar to what KVM does, where if you're doing a live migration, you start tracking the dirty memory, you copy the dirty memory, you let the VM run for a while, you copy the next dirty memory, and eventually you converge into a small amount, you stop the VM, you stop the DMAs, and then you migrate everything. This goes hand in hand with the VFIO support for live migration of PCI devices. And this implementation is done using the system IOMMU. So it's generic. If your processor has the feature, then all of your IO devices can make use of it if they support VFIO PCI device live migration. Then the stuff that I've listed here that we haven't got done yet is the IO TLB invalidation forwarding. So if you have a page table in user space and in guest memory, you still have to forward invalidations. Like when I change the IO PTs, I have to forward them into the actual hardware. We haven't quite finished that API yet. It's a little bit fussy. On the topic of invalidation, people want to make that faster. So the next hardware innovation is we can give every guest its own command queue, and we can put a DMA command queue directly in guest memory, and the guest can just poke the invalidation commands into the command queue, and the hardware can DMA them, and we don't have to do a VM exit to do an invalidation. Invalidation is a performance path for IOMMU workloads, so optimizing this is really critical. IO events, all the IOMMUs can generate events. When things go wrong or when things are need attention, the classic event is a page not present. So if you're doing shared virtual addressing, you're doing PASID, and you're doing something called PRA, which is page request interface in PCI, when you hit a non-present page in your IO page table, the IOMMU will generate a page not present event in the hypervisor hardware, and it has to be forwarded to the guest so that the guest can receive the page not present event, populate the IO PTE in guest memory, and then issue some invalidation so that the hardware can be restarted and actually do the DMA. And this is a critical piece to doing the virtual SVA component. There's patches on the mailing list. I saw they were just posted today, again, like V7 or something, to get closer towards this. And the final one I've listed is the concept of allowing the KVM page table, I guess it's called the EPT in this case, to be just pointed at by the IOMMU hardware. Most of the hardware architects these days have arranged the IOMMU page tables to be the same memory layout as the KVM page table. So why do we have to have 2 copies of it? Why do I have to do all this mess to do it when I can just use the KVM page table? This looks like it might become important when we start to talk about confidential compute because of, security reasons. You don't want to have 2 different, you don't want to have 2 hypervisor controlled mappings of the confidential guest's memory. But I don't know yet. That's another conference topic. So here's some short summary of the patch series. It kind of repeats what I've said now. We got a lot merged since the last time I stood here. And we got a whole bunch more stuff in V6.7. It's got the dirty tracking, which is really good. I'm hopeful that the IO page table invalidation will reach 6.8. Fault delivery, I haven't looked at it too closely yet, but it would be great if it made 6.8. And the passive support, SIOV support, and all the other pieces are kind of a little bit out there, like the things that we know that we want to do, things that we've been talking about, but I haven't seen too many patches as we go down the list, or the patches are like kind of wobbly. SIOV support in particular, there's work afoot. There's an industry consortium at OCP that's trying to make a standard out of this. So that might change quite radically what we want to do in the IOMMU and what CPU vendors are building. And the stuff about the interrupts is, I'll talk about later. It's kind of a big thing. Feel free to interrupt, of course. This is Plumbers, so it should be interactive. So here we're getting to the more exciting stuff, so what do we need to still do? The PCI peer-to-peer is my perennial bane of my existence. I keep talking about it, and I never come up here and say, yes, we got something merged to advance it, but we're getting close this time. I know it. I've got people working on it. This is challenging because the DMA layer doesn't really support peer-to-peer without struct page memory today. There's actually just no way to do it. And Christoph likes to remind me every time I post a new patch that it can't work, and it doesn't work, and he can't do such a broken thing. So we need to make it so that DMA buff works correctly before we can merge the VFIO support for DMA buff, before we can merge the IOMMU UFD support for DMA buff.
What does work correctly mean in this context?
That's a very good question. I'll channel Christoph a bit here. He would like, so today, if you want to DMA map something for PCI, you have to call like DMA map page or something like that. But you can't call that because you don't have any struct pages. This is IO memory, it's struct page list. So today people like to hack that and they call DMA map resource. But DMA map resource is not appropriate for P2P memory. It's supposed to be for something else yet again on ARM or something. So DMA map resource doesn't know the originating PCI device, so it cannot compensate for the PCI offset, and it cannot compensate for ACS anomalies in the system, which are important for the general case of P2P. They're not important for hooking up the IOMMU, but we can't do something so narrow with VFIO and DMA buff. It has to support all the general cases. It has to work with RDMA as well. So we need a new API of some kind that's like DMA map P2P with a PCI device and a whole bunch of other mess. And that already sort of exists. It's built into the DMA map SG system, and my brother actually did it with the zone device P2P infrastructure. But it only works if you have struct pages, and we can't create struct pages for VFIO because the bars are too small, because S390 doesn't support it, because. So.
Okay, yeah, my question was really, are you foreseeing having to create struct page allocations?
No, we're desperately trying to avoid that.
Cool.
That's why it's so hard. If I could do that, I could do it right now. I would have no problem. So, VFIO update vAdder. It's this horrible thing to let you re-exec QEMU. The person who wrote it promised me they'd make an implementation, and they never did. So it's still open. Our RNO was something on my slides from last year. We didn't do it. This is like really like fine refining the API. I'm not sure if it has value, but if people want to use the compatibility, maybe it does. And Power has not improved at all. I was so close to being able to delete it because it had been broken for like 8 months. I was very close to being able to delete it, but someone fixed it. So it's, yeah.
So close.
Yeah, I feel your pain. So here's my like, let's collaborate, let's talk about the things. So number one, whoops, I think I have slides for all of these. This is just kind of maddening. So we went as I talked about earlier, one of the key things to achieve here is virtual SVA. So something like DMA engine, I guess, is what Intel is pursuing inside a virtual machine that can do DMA directly to the CPU, to a process address space with very little overhead without having MMU notifiers or other kind of mess to do mirroring. And that requires PASID, it requires PRI, it requires ATS, it requires all this virtual IOMMU stuff. The PCI spec decided that PASID would be declared in the config space using a PCI capability structure, but only in the physical function. So the virtual function doesn't have a PASID capability block, and it's very hard to change config space to insert things into it because it's very poorly specified, like what is valid, what is being used by the device, what is not. So if you want to assign a VF that has PASID capabilities, QEMU is going to have to insert a capability block with software, and it's going to have to figure out where to put it in a way that doesn't break the device otherwise. And this is a mess. I think we kind of came to an agreement that Alex suggested we should just do it in QEMU and accept that it's a mess.
In confidential computing has a similar problem where we want to enumerate properties and we don't have config space. And I know that we have concepts like ACPI companion devices for firmware tested. Do we need a virtual companion device concept where we can just put whatever we want there, annotate so that the thing can annotate features, and we don't have to, we stop trying to find config space for things?
I don't know. I'm the wrong person to ask about ACPI. I'm not an ACPI.
Well, so it wouldn't be ACPI, but I'm saying this is something. This is my agenda. I want to build something for confidential computing, and it would work for this too.
It would. It does sound nice. I also bounced the separate idea off of some of our PCI SIG representatives. I said to them, could you standardize a config space, a capability that was simply empty, right? And then my devices that want to be compatible can give you a chunk of empty, and Bob's your uncle, you can put your confidential compute, I can put my PASID, and we can all just use it. So perhaps, given your similar problem, I will ask to see if that can become percolated up to PCI SIG, and then talk to your PCI SIG reps, and maybe it's the right thing to do.
Static config space, you can just leave a big gap. You don't need an explicit capability for it if you just want a device that can definitely have space to insert this.
Does more space solve the problem that you don't know how the space is laid out?
For extended config space, you've always got a next pointer.
Yeah.
So as long as the next pointer has a sufficiently big gap.
the mic to Alex.
There are lots of devices that hide registers in config space outside of capabilities, and that's essentially what we're afraid of stepping on. We don't know how they're used.
Yeah, that's the justification right there. Like without the device. Yeah, that was.
There are a lot of broken devices.
Yeah. And, I think my company makes some, so we'd rather not. Yeah. Okay.
Sorry for this. It sounds like, Dan, what you're asking for kind of sort of is a paravert interface. And the hard thing about paravert interfaces is you have to get a guest that is updated to be able to talk the paravert interface. And with that, it doesn't usually work as a general purpose solution. For confidential compute, you can kind of force people in that direction because they're already enlightening the guest. But for a general purpose, it's really hard because you're waiting not 10 years, you're waiting a couple years for the guest to catch up. And in the meantime, you want to ship hardware that the guest can use. So it's a not perfect solution.
Yeah, that's exactly right. So we'd like to stick, so the greatest extent we can have. I touched on this earlier. So the invalidation is the cleaning out the IO-TLB. So the interesting thing about this is that the caching hardware in IOMMUs is that every implementation is different. Everybody's put different things in their caches. They've cached different objects. They call the objects different names. It's just kind of crazy, the variety. When you expose to the guest all these objects, so they have the objects now in guest memory and possibly even confidential guest memory, the hypervisor has no idea what's going on. Like, no idea whatsoever. So the guest changes some memory and it needs to issue the correct set of invalidations for the change that only it knows that it made. And the original concept here that I think Eric probably came up with was to have this very generic concept of invalidation. And we ended up having like 17 different invalidation modes that did the cross matrix of all the possible combinations of all the different things. And I pushed back against it. I said, no, we're just going to forward the actual hardware invalidation commands. If you're emulating, Intel hardware, then you'll get an Intel hardware invalidation command that tells you exactly what to invalidate in Intel's language. You'll translate some of the IDs, and then you'll push it to the real hardware. And that's just how it is. That's the best way to handle this. That way we don't over or under invalidate in any case. And my example here is like ARM is very easy to understand. There's a address space ID, which is completely private to the guest. And the guest decides which page tables it gets associated with. And when the guest changes an IO PTE, it generates an invalidation for an ASID. And the hypervisor has no idea what that's for. It has no idea what that ASID is assigned to. It has no idea what guests or which PCI functions is assigned to. It just has no information. This is further complicated because there's actually two IO TLB caches. There's one in the CPU we usually call the IO TLB, and then there's something in ATC called the ATC cache. So this is on the PCI device where it's also caching IO PTEs inside the PCI device, and you have to do, in all the IOMMUs, there's two invalidations you have to do. You have to invalidate the CPU, and then you have to do another invalidation to invalidate the remote device. And they use different identifiers because you invalidate the IO TLB using something like the ASID, and you invalidate the remote device using its RID. And again, only the VM knows how the RID and the ASIDs and everything else are all mapped together. So it's just...
Well, at least the PCI one is standard across ARCH.
At least it is, yes. At least that one is standard. So this is what we're going to. I think this is what the current patches are. Nobody's come up. The biggest objection to it was because of VirtIO IOMMU. VirtIO IOMMU wants to expose some of this mess to the guests, but it wants to have a VirtIO standard language to manage the invalidations. But they are not at the point of being able to do all the VSVA passage stuff yet, I think, for all the nesting combinations. So I offered to them when they get there, we can solve it. We can do something. I think that's reasonable. Sorry? Oh, I can't. I'm sorry, I can't see it. It's okay. DVSec. That's a good idea. I'll put that in my guy's mind. Driver modernization. This is going to kill me, I think. There are so many patches for this that are progressing in various states. So as we developed IOMMU FD, and as we've done cleanup to the IOMMU subsystem, we kind of subtly changed the way the driver operations work, especially the domain operations, and we've restructured how the drivers work, and we've given the drivers more tools to make use of than they used to have. And now we have this set of kind of 10 things that an ideal perfect driver should do when they implement their flows, and currently none of the drivers do all of these 10 things. I have like a 65 patch series that fixes ARM SMU v3 to do, I think I got all of them. But they all kind of tie back to IOMMU FD and VM emulation. If you're emulating a IOMMU in an arbitrary guest that's not Linux, maybe it's Windows, maybe it's something else, we don't know what it will do and we don't know how it will operate. So if that guest expects to have things like hit this identity, then it should be possible to relay it to our physical hardware and keep it hitless. If the guest thought it was hitless, let's not break it. Just on the basic premise of if we're doing hardware emulation, we should emulate the hardware without gaps. Some of this stuff is security. Like when I was going through the ARM driver, I noticed that it accidentally turned on an identity domain for a tiny little time period when IOMMU FD would do certain things. So if you could exploit that race, you could DMA into any kernel memory. Oops. That's kind of crappy. So you don't want some of these things. And we had an early implementation of SVA that got merged into the ARM driver that doesn't match our current domain-centric language that we're using. So that also has to be untangled and ported over to a domain-centric implementation, and then broadened to have generic passage support. The drivers, the only drivers that implement passage support today just didn't use the API at all. So there's all kinds of gaps where we have this nice API at the core level, but you can't actually use it because if you try to use it, the driver doesn't implement it correctly or implements it in a weird way, or it has all these weird limitations and restrictions. So there's patches on the list, a lot for ARM. AMD's got a 4 or 5 part series they're working through to get to, I think they do like 3 or 4 of these, but they get very close to the rest. Intel's been grinding through as well. They have the SVA and the passive pieces, I think, but they need some of the other ones. And then there's all the other drivers that I'm ignoring. They're going to have the wrong API. They're just going to be what they are, like all the weird embedded stuff. If you use it with IOMMU FD, it will work, but you might have, like, I can't guarantee that you won't hit like a bug in the driver where it's not secure or anything. You know, buyer beware, I guess. Try not to use those things. The interrupts. So this is a big problem. That's a big amount of work to fix. ARM and Intel have diverged in how they handle interrupts with the way it relates to the IOMMU. Intel platforms say that there is an MSI aperture. It's decoded before traffic hits the IOMMU, and we always capture MSIs. ARM said there's an MSI aperture. It's after the IOMMU. You have to translate through the IOMMU, and then you have to end up in the physical aperture. Oh, good. So this difference is exciting. Unfortunately, the entire interrupt architecture in VFIO has been designed around Intel and what Intel can do, not only what Intel can do, but what they could do like 10 or 15 years ago before they had VTD and the interrupt bypass and all that other great stuff. So none of it makes any sense. None of it works the way it's meant to work. And ARM ends up with this really ugly kind of hack to make it not be completely broken so that you can use VMs. But when we get to things like confidential compute, this isn't going to hold up. This is just going to break in so many ugly, ugly ways. And even today, it's very hard to get this working because of the way the kernel's plumbed everything through. So what I would like to do, what I would like to start getting towards is a world where interrupt isolation is done with interrupt remapping. So we do not have to hypervisor trap MSI programming. The hypervisor, the device in the VM can program the MSI directly. It can program the MSI directly because it has interrupt remapping hardware, has virtual interrupt remapping hardware that's actually gone and set up the interrupt. And that's where the hypervisor interaction would be to configure the interrupt remapping hardware and set up the VTD magic and all the other stuff.
So this solution that we are currently having is based on the ACPI RMR one. And I think that still has an open item because the RMR mandates that the configuration that the firmware sets is preserved in the Linux kernel. There is a DSM-5 checking, basically. So that breaks some of the IOMMU device assignments because I think Lorenzo might be aware of this. Like Eric mentioned that when he had this series, guest with devices where IO port address ranges are below 1000 or something, the Linux kernel always re-enumerates, and those cases were broken. So
okay, I haven't heard about this, but that
so
sounds great.
One more thing is before proposing this RMR-based solution, Eric had another method of solving this, where he was plumbing a few more APIs to bind the guest MSI to the host. So it goes all the way and then does all the mappings.
Yeah, see, I'd like to avoid creating more mess, right? The right way, like certainly, you know, if you talk to ARM architects, the way they imagine this works is there's a nested GIC and it does the interrupt remapping and then it just takes care of everything. And that's how it's supposed to work. And I'd like to drift towards that architecture because I know that we're going to need it when we get to confidential compute and other things. Like you won't be able to do some of the tricks that you're doing today. You won't want to do some of the tricks you're doing today. And to me, that means you remove the trapping of MSI programming and you rely on interrupt remapping or GIC or whatever your architecture is providing to give you that. And I'm hopeful that this will start to, you know, I hear other companies building hardware talking about this as well, and I'm hopeful it'll sort of move into a direction, but it's a huge task. I mentioned it, I think, to Mark once in a thread, and he's just like, yeah, you go do that, good luck. I'm like, yeah, okay, well, we're going to have to go do that at some point. I'm kind of hoping to get ARM nesting working without tackling too much of this.
So, Jason, just to make sure I got what you meant, you want the guest to be able to program the interrupt controller so that the IRQ is directly injected into the guest instead of and programmed through the page tables. Is that what you want, to be transparent without trapping to the host?
Yeah, so like in ARM terms, the MSI is programmed with the address of the ITS page, which is entirely controlled by the guest, which is the origin of this problem. So the address of the MSI page is entirely controlled by the guest, and only the guest can tell where to put it. And then the data is basically the index of the virtual GIC, right? Yeah. Because the GIC will decode using the virtual RID, and then you'll get the data as the final piece of it, like the MSI index. So there is no reason to have hypervisor trapping if you've got a virtual GIC, virtual RIDs, and you can set the ITS index, and all of that piece works the way it's meant to. Did it make sense?
Maybe we can take it offline, but yeah.
Okay. Yeah. I think the issue, I haven't delved into it enough to speak competently about what the issue is on the software side, but I gather that the way we manage the virtual GIC is not really as comprehensive as maybe the full-blown, like a full-blown emulation of a GIC. It's like some cut back one or something. Am I almost done? Dirty tracking. So Zhao asked me to include some of these for him. So pursuant to the earlier discussion with Pasha, there's a whole bunch of stuff. There's a whole bunch of more smart algorithms that people want to cram into the IO page table stuff. And they're generic. Like every single IO page table format needs to have the same algorithms. I need to have a way to make the IO PTEs bigger and smaller if I have continuity, because dirty tracking is based on the IO PTE page size. So, if I boot my VM with 1 gig pages, that's great. I'll get really good IO TOB performance, but my dirty granular QEMU level is 1 gigabyte. That's no good, right? So I want to take my 1 gig, and when I'm doing live migration, I want to chop it down to 2 meg maybe, or down to 4K. And then when I'm done, I want to make it bigger again. So this is generic. Like there's nothing unique to any of the architectures about this. It's all generic code. It's like code doing fancy things, complicated things. Zhao also wants to improve the performance of all of this code. It turns out that it's not written optimally. It's like not an optimal radix tree walker algorithm. It's written in a simple way. It's not efficient. We can do a lot better if we, take smart algorithms that we know how to build. We know how to work with radix trees efficiently. So like Zhao has already posted some example patches of how to do it for AMD. And that's great, but you know what? There's 7 other IO page table implementations that are also not efficient. So at a certain point, this doesn't scale. Like this having everybody code their own algorithms doesn't scale. We have too many algorithmic needs that we can address with common algorithms. We need to get to a point where things like map, unmap, split, grow, and shrink are done in common code. And like the there's a series of macros and other things that let you work with the radix tree, because the radix tree is conceptually all the same. And we know that this approach works because the demonstrates that it works across all the architectures that it supports. So I've had this in my head for a while, but it's such a big and scary task. I haven't even thought about starting it, but
we looked at doing the same thing in KVM, and my advice would be do it as soon as you can, because the longer you wait, the harder it is.
Yeah,
and that's what we ended up with.
We're already at that point.
Yeah, like we wanted to do it to at least start with ARM and x86, and then we got into ARM's ARM's different behaviors with respect to invalidations, and then that just, we have code that works today. Why do we want to change it? And so sooner better.
The problem, the challenge with the IOMMU IO page table stuff is that it was abstracted and sort of put into a box and made shareable. It was done so that the GPU drivers could use it. So there's a whole bunch of GPU drivers calling into the same code. There's a whole bunch of IOMMU drivers calling into the same code. And to really do a good job here, you're going to have to touch a lot of call sites, a lot of places. And I get little shivers sometimes when I think about changing DRM code, because I'm not a DRM person. But I think it could be tackled. I think we can do a really good job. And I see a lot of people talking about things that really, really demand doing this, because otherwise I was talking to someone the other day and they say, I want to do some feature. I'm like, yeah, you'll need to do that. No, every page table walker, what architecture are you interested in? ARM, AMD, Intel. Oh, okay. That's 7 different copies of that thing that you want to do, because every one of those has 2 versions of the page tables that the IOMMU support. And you have to do it for all of them. Like, it's just intractable. It's completely intractable at the current point to fix any of this stuff. So maybe this will be a project for 2024. We'll see if I've inspired someone to tackle it in this room. Yeah, because I'm speaking very inspiring here. The last idea is I think it's fantastic, but if you have, so PCI has this concept that I talked about before called PRI, page request interface. So if you can do a DMA to a page, you can get back a not present, and then the device will stop what it's doing and it will ask the operating system to put the page back, right? This is used for SVA, but you could also use it for dirty tracking. You could make all of the IOPTs not present and just let the device start to fault them. So it would provide the opportunity to have kind of a 2-level scheme where you could use the fast dirty bitmap bit, and then when you get to like the end of the migration, you could switch to this much slower, much more expensive PRI-based mode and really like both throttle the device, because you can control how fast you respond to the PRIs, and also get very granular data.
Is PRI analogous to write protecting versus dirty logging?
Yeah, it's kind of like you can do write protecting, you can do not present as well. So
Okay.
you can do both.
So for the so what we've observed, so Google internally has had a dirty logging based thing where it would go and you would just use dbits, and then you'd go and reap all the dbits and blah 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 blah. And we're actually switching to a pure write protection based scheme. And what we found is that if you can get your how to phrase it, if you can make your user space smart enough and you have fine enough granularity in which ranges you are write protecting, you can achieve the same performance without having to have the CPU overhead of going to go reap all the dbits. So if you have something like PML, even that gets you kind of close, but then there's complexity there and it may not be available on all hardware. So long story short, you may not even need, it's feasible to do just a PRA-based dirty logging, like across the board the entire time.
That's interesting. I wonder what, when you said performance, what performance were you measuring? Like VM
Yes,
operating performance?
Everything.
Everything?
So the things that are, like the number one thing is guest jitter. So making sure that we're not disturbing the guest too much and a bunch of stuff there. Yes. But then the other side of performance is there's trade-offs. If you're spending a bunch of time and you're not generating guest faults because it's just updating dbits, then you have to spend CPU time to go and grab those dbits, and that introduces guest jitter because you're taking CPU time away from them directly. Right. And then you just also have, if your guest isn't necessarily dirtying a bunch of memory, you're spending time looking through the page tables to get dbits where nothing has been dirtied. And so like in KVM, you can start to do schemes like if you have dbits higher up the page tables, and so not just at the leaves, then you can optimize some things there. But I don't know if hardware has that. So all of the above in terms of performance, and we've been able to, we're not there in production yet, but we are trending in the direction of being able to deprecate our dbit dirty logging entirely and just going pure write protect with enough smarts to not blast everything.
That's encouraging.
I will add that PRI is a lot nastier than a normal page fault from a performance point of view. There's a whole load of transactions.
PRI is completely devastating for DMA performance. Completely devastating.
You can have devices that will abandon what they've been doing for the last 10 minutes because one of these faulted.
Yeah, it depends on the device. And 5 minutes.
Let me caveat the KVM side of this with, we have a fast locklet, like true lockless, super fast path for propagating the write protect faults, fixing the fault, and getting that information into a dirty log. So it's under presumption that your fault is fast and not destructive.
This is awful. The faulting is awful. You'd be horrified if you understood what the devices did to make this work. The other sort of wrinkle here, and I didn't add the slides to it, but like what I talked about earlier about sharing the EPT, there is a wrinkle in PCI land where PRI and ATS are not, devices have different kinds of DMAs that they want to do. Like maybe I'll support PRI for these DMAs, but I'm not going to support it for those DMAs, which is delightful. And part of sharing the EPT would require using PRI to fix up all the missing faults and stuff. So to make this work on real hardware that actually exists, we need some way to teach the system that the device can't do PRI in this chunk of memory. So you have to make those pages present at all times. And I'm not sure how we'll get there, but it's something that we're actively starting to think about. I guess we're probably on the last set of questions here.
Yeah. So for dirty logging, does it make sense to have somehow the driver tell the hypervisor, I'm going to write this, please, like do some kind of dirty logging with driver and enlightenment in the guest, so that the PRI is kind of the last resort, but actually you already know in advance that some pages are going to be written?
Yeah, I have not heard anyone researching that, but it does kind of make sense. Like, you know, especially if you were sharing the EPT, I've heard people talk about things like, oh, well, you know, we can kind of pre-dirty things because the guest has already dirtied the memory or something like that, and sneak things along. But I'm not aware of any active projects in that idea. All right, thank you.
Thank you, Jason. And just thank you very much for attending, and I hope you enjoyed it. Thank you very much. Bye.
You're good? You need to close the room. I'll do this. We are kicking everyone.